speaks about the economics of battery production, detailing how costs have plummeted thanks to the economics of scale and technological innovation. Um, from there, we discuss about electrical vehicles. How does it reach a price parity with the internal combustion engines, considering both the purchase price and the total cost of ownership. Once we have established the economic context, we focus on the technical side of it, looking a bit more deep about the lithium-ion battery and how it works. We look at the emerging chemistries like sodium-ion, lithium manganese iron phosphate, silicon anodes, solid-state cells, lithium sulfur, and lithium air batteries. Then we turn to grid scale storage technologies, long duration batteries such as vanadium redox flow, iron air, and liquid metal systems. Then we examine critical minerals, how the demand is growing, where the suppliers are located, and why chains are vulnerable at the moment. Then we discuss of the direct lithium extraction methods and other breakthroughs in mining of these critical minerals, as well as the geographic distribution of the mines and refineries. Then we assess the shifting geopolitics around the critical minerals, exploring export controls, trade agreements, and resource nationalization. Finally, uh, we address the environmental and social impact of these critical minerals, policies and regulations, recycling and circular economy strategies, and future research directions. Um, so that's pretty much it. That's the agenda today. So coming to the importance and motivation for this seminar, the energy transition depends on electrifying transportation, heating, and industrial processes. And batteries are the cornerstone of that transition. According to the International Energy Agency, demand for lithium surged nearly 30% in 2024, while demand for nickel, cobalt, and natural graphite rose between 6 and 8%. Roughly 85% of this demand growth came from the energy sector alone. These statistics underscore how quickly the battery market is expanding. Examples illustrate the momentum. Like for example, the Norway's EV adoption is a very good example, which surpassed 80% of new car sales due to the tax incentives and widespread charging infrastructure. The California is another example, which relies on battery storage and pumped hydro to stabilize its solar heavy grid. So something you need to know about the grid storage, which we'll discuss a bit more detail later on. That's one of the areas where it is growing really fast in terms of battery adoption. That's to normalize the supply and the demand, which is one of the key areas where the coal power plants and gas power plants are currently being used, which can be turned on quickly and turned off, unlike the nuclear power plants. So battery play a very vital role in normalizing the grid demand and supply at any given point of time. Um, then, however, rapid growth also exacerbates existing vulnerabilities. The top three refining countries account for more than 85% of refined critical minerals, leaving supply chains heavily concentrated and prone to disruption. This concentration confers geopolitical leverage to producer nations and exposes manufacturers to price volatility. Sustainability and ethics are equally important. Say, for example, cobalt is often mined under hazardous conditions in the Democratic Republic of Congo. But that's where most of the cobalt is currently situated. And the lithium brine extraction can deplete scarce water resources in South America, where lithium is highly concentrated, but it uses quite a lot of water in terms of the brine extraction. Um, s- um, the indigenous group in Chile's Salar de Atacama, who must negotiate between economic development and water rights, illustrates the human dimensions of the battery production. So there are pockets of societies in the world where the extraction of critical minerals for the battery does impact their water resources. So while the critical minerals for the batteries are key for the development of the global economies, we should also be mindful about the human impact that it brings and how to navigate using technological innovations. And environmental degradation, labor practices, and community consent is essential to a just energy transition. Finally, batteries play a vital role in enhancing energy security, enabling distributed generation, and fostering a resilient, decarbonized grid. So that's the whole motivation behind why we are moving towards a future where battery plays a vital role in the green energy transition. So this slide examines how economies of scale, manufacturing innovation, and commodity cycles have driven down the battery costs over a period of time. In 2010, a typical lithium-ion battery pack costs around roughly like 1,000 US dollars per kilowatt hour. By 2022, prices fell to around 153 US dollars per kilowatt hour. You can see such a massive drop in the price within a decade. And 2023 saw a further drop to around 149 US dollars. Analysts forecast pack price of roughly 111 US dollars in 2024 and as low as 80 US dollars by 2026. This is an industry forecast based on uh, innovation in the package and packaging methods, electrical equipment innovations, the cost of the raw materials going down, economics of scale. So everything is contributing towards this forecasted price by 2026. The Bloomberg's NEF, which is one of the key forums where green energy and transitions and cutting edge technologies are discussed, it does a survey in 2025 which finds that average pack price are now 93% lower than it was in 2010 at about 108 US dollars per kilowatt hour. Costs may vary by the chemistry of the particular battery being used. Like for example, lithium iron phosphate packs average of 81 US dollars per kilowatt hour, while nickel-rich NMC nickel manganese cathode packs remain higher at around 128 US dollars. That's mainly because the iron ore is much cheaper than nickel and manganese. 60% of battery costs comes from raw materials, particularly cathode metals. So commodity prices have a large impact on the overall price of a battery. Falling metal prices, increased automation, larger factories, and innovations such as cell-to-pack architecture contribute to cost declines. In cell in cell to pack designs, which is what you see in most recent Teslas and BYD cars, cells are integrated directly into the pack, eliminating a modules and saving space, weight, and costs. So a combination of these innovations is driving the cost of the pack level costs per kilowatt of batteries down very quickly. How learning curves, so like for example, each time cumulative production doubles, unit costs fall by about 80%. So the learning curve over a period of time is increasing. So a feedback loop in terms of the battery production is also contributing towards more innovation within the design of newer batteries. Say we can give a Tesla's Gigafactory in Nevada is as a good example that benefits from the economics of scale because the factory is so huge. It reduces supply chain time delays and also a vertical integration within the same floor of the factory, which increases economics of scale and advanced automation on a vertical scale, which is a very good example. And also another example would be CATL's Chinese mega factories, which leverage the government support and local supply chain to reduce logistical costs. So in any typical battery production, logistics uh, plays a vital role in not only in the time it takes to produce a battery, but also the costs of per kilowatt cost of the battery production be more integrated within a common factory floor space for battery generation would reduce the costs over a period of time. So a lot of learning curves within the last decade is contributing towards more innovation, more vertically aligned battery production, and even the most recent changes is making battery producers like Tesla and CATL to own the mines and also the supply chain from refining up to the battery production. Um, so another innovation which I would like to mention is about the BYD, which has pioneered the blade type batteries that integrates cells into the structural packs, further reducing the cost and improving the safety. Innovations in manufacturing also plays a vital role in the cost, bring down the cost. Like for example, dry electrode coating, which eliminates solvent recovery and saves energy. Uh, Quality control during the battery production also contributes towards the yield of the battery in terms of per kilowatt hour, and also the wastage and the overall price of the battery. So the more recent advancements in the AI is helping in performing quality control in a much precise manner, which reduces defects. So the overall percentage of yield per kilowatt hour has been steadily increasing in the last decade. Machine learning algorithms are used to optimize process parameters in real time rather than in batches, like how it used to happen in the past. So you can see a graph here which kind of shows you from around 2010 how the battery price has fallen within the last decade and a half. So in small pilot plants, overhead and labor represent significant shares, while larger gigafactories, the raw material cost dominates the overall battery cost. Economics of scale are essential for to produce affordable EVs in the future, and that continue investment in large-scale manufacturing capacity will remain a key driver of price decline over a period of time. So in this slide, let's discuss about electric vehicle and the internal combustion engine and the price parity between these two over a period of time. And as battery costs are falling, as we have seen before, Electric vehicles are closing the price gap with internal combustion engines, and this is happening at the moment. Analysts predict that by 2025, just this year, the average EV battery pack will cost around 199 US dollars per kilowatt hour, which has been achieved in certain manufacturing sectors. Uh, because battery packs account for roughly 30% of a mid-sized EV, electric vehicle manufacturing cost, this decline brings electric vehicles close to the price parity with the gasoline car, which is petrol or diesel, even without the subsidies. So currently, a number of countries are providing subsidies to promote electric vehicles. So what the research is showing is that even without the subsidies that the government is offering, the price parity with the internal combustion engine is happening with the electric vehicles because of the drop in price of batteries per kilowatt hour. In terms of the total cost of ownership, many electric vehicles are already cheaper due to the lower fuel and the maintenance costs compared to the internal combustion engine vehicles. Breakdown, so the difference between the upfront cost and the lifetime cost uh, is normalized over a period of time. So when we look at internal combustion engine cars or vehicles, the upfront cost might be a bit lower. However, the ongoing maintenance and the fuel costs over a period of, say, 10 years will add up. Uh, so if we have to compare the price parity, we need to compare not just the upfront cost, but also the total cost of ownership. EVs have higher purchase price, as I told you, but lower operating expenses, as electricity is generally cheaper, especially if you have solar to charge the batteries, than a petrol and electric drivetrain, which requires less maintenance. And also, there is a geopolitical aspect. For example, any supply side shocks of uh, uh, petrol or diesel fuels due to global changes may not really impact an electric vehicle which is charged by renewable energy. A 60 kilowatt hour battery in an electric vehicle might cost around $45,000 today versus a comparable internal combustion engine, which is around $35,000. But the EV electric vehicle saves $1,200 per year on fuel and maintenance, recouping the premium in 5 to 7 years as of today. In markets with high fuel prices and generous incentives, parity occurs sooner. Norway, which is a very good example, offers VAT exemptions, reduces tolls, and grants access to bus lanes, making electrical vehicles not only cost competitive but also more convenient. In United States, federal tax credits, state rebates, and Inflation Reduction Act's rules linking credits to domestic battery content or accelerating the parity between the ICE and the electric vehicles. Um, Smaller cars achieve the price parity much sooner because they require smaller batteries, like for example, a hatchback, whereas a pickup truck or a luxury SUVs or a truck which needs a larger battery pack, delays the parity by further few years. So this is why the scale of production and the competition is much important for battery production. So we don't have fewer producers of batteries. If there's more competition, this because of the economics of scale, the price might come down much sooner, which means the number of years takes for the price parity between ICE and EV comes down as well over a period of time. So as more and more automakers enter the electric vehicle market. The competition drives innovation and cost reductions. So the price power parity is not just about batteries, it also depends on the reductions in the cost of power electronics, which is something being taken into account nowadays because if you look at the pack level price of a battery, it's not only the actual batteries but also the power electronics which goes along with it, like inverters and switches and sensors and other electrical components. Um, Advanced materials and streamlined assembly process are making the cost of power electronics to be reduced over a period of time. So there are certain uh, advancements in the materials of the power electronics, like for example, gallium nitride is one of the advancements which I can think about. So that used to be used only in space research, rockets and satellites. However, it is getting into consumer electronics and into the battery power electrical components lately. And over a period of time, this would reduce the not only the cost but also increase the life of the power electronics and reduce the weight of the power electronics, which in turn will reduce the overall uh, kilowatt hour cost on a pack level. New business models that lower barriers to ownership, such as battery leasing, subscription services, vehicle to grid. So these are some of the newer methods of ownership of electrical vehicles, especially the battery. I would give you one good example is Renault Zoe car, which I would say a good example in Europe, whereby you own the car but not the battery. The battery is being leased from the company, and over a period of time, you can get the battery replaced from the company. So this also kind of reduces the overall cost of ownership of electric vehicles and subscription methods for a number of two-wheeler based electric vehicles, which we have seen in a number of Eastern Asian countries, and a vehicle to grid revenue streams, which is being undertaken by few electrical companies, whereby when the renewable energy is much cheaper during the day, it gets dumped into your battery pack of parked car, and when it's more expensive, the grid will automatically take it back from your vehicle. So that's a new technology which is streamlined, which is kind of crowdsourced for to normalize the grid rather than using coal power plants or gas power plants to switch on to normalize in peak demand times. So these are innovations that's happening and help consumers overcome the high upfront costs and accelerate the adoption of electric vehicles. So, when we speak about electric vehicles, we should speak about the lithium-ion chemistry, which is the fundamental chemistry being used in almost all the electric vehicles, although some newer chemistries are getting advanced. And lithium-ion has been the go-to battery chemistry for a number of years now, well tested, and the chemistry has been gone through a number of cycles and is well understood by the market. So, on average, lithium ion, in terms of energy density, it's around 150 to 260 watt hour per kilogram, and the cycle life of lithium ion is 1,000 to 3,000 cycles. The costs are declining. Like for example, it's around um, 405 dollars per kilowatt hour installed in the grid, but dropping rapidly. And 87% of lithium consumption currently globally is going to only for batteries. So lithium-ion batteries works and why they have become the dominant rechargeable technology in the world. It's because a cell consists of a graphite anode that intercalates lithium ions, a cathode made of lithium metal oxides such as lithium cobalt oxide, NMC, or lithium iron phosphate, a microporous polymer separator, which is the separator over here, which is the white band you see here. So, which is soaked in a liquid electrolyte, and copper and aluminum current collectors. So during a discharge, lithium ions migrate from the anode to the cathode through the separator, while electrons flow through the external circuit. So during the charging, the process reverses. So lithium ions de-escalate from the cathode and intercalates into the anode. So the energy density of a modern cells range from around 150 to 280 watts hour per kilogram, depending on the chemistry and the design. Nickel-rich NMC cathodes, for example, the NMC 811, offer higher energy density but rely on nickel and cobalt, whereas LFP offers lower energy density but superior safety, longer cycle life, and lower cost. So, due to the variety of chemistries currently available, the industry is choosing based on the application what chemistry to use. For example, a nickel and cobalt, which are quite rare earth materials, and it predominantly comes from Congo, and that's mostly used for critical applications where the energy density is much needed. For example, your cell phones is a good example, laptops are a good example. Uh, that's where the nickel and cobalt chemistries are used. However, the applications where space and weight size is not a big concern. However, a longer life cycle and the overall cost of the battery installation should be lower. And that kind of application, I would say, energy grid, power banks for a factory or an office or a building, um, even trucks like heavy duty, long haul trucks. So these kind of applications, LFP batteries, kind of becoming a go-to chemistry nowadays. The role of a separator is basically it prevents the electrical contact between the electrode while allowing only the ions to transport. For safety, separator must retain their mechanical integrity and shut down the cell if overheated. A liquid electrolyte, often a mixture of organic carbonates with a lithium salt such as LiPF6, and um, that additives improve stability and suppress dendrite growth. So dendrite growth is a problem within the battery chemistry, which has been encountered by the researchers for a number of years now, whereby when a battery ages with more cycles as it ages, if it goes through multiple cycles, it forms micro cracks within the separator, which is called dendrites, and um, there could be charge leakage, which could short circuit between anode and cathode over a period of time, and that's what was causing fire and thermal rundown of the batteries in the past, where you have seen sometimes news showing that electrical vehicles catching fire, and if a nail is pierced, it catches fire and everything. But over a period of time, the industry and the innovation and the research has understood that changing the separator chemistry, you can reduce the dendrite formation, not completely. However, you can delay it, and more cycles can be used. Likewise, the thermal rundowns were managed using thermal management systems. For example, in BYD and Tesla, and even Hyundai, Kona, and other electric vehicles, they use heat pump to extract the temperature from the air around the car, and to maintain the battery, and also inside the cabin of the car, and maintain the battery's temperature, an optimal temperature, so that whenever it charges, it's conditioned so that it doesn't form, it doesn't cause a thermal rundown over a period of time. Um, so in terms of liquid electrolyte, which is often a mixture of uh, organic carbonates, uh, it plays a vital role in terms of improving the battery chemistry, and also it's prone for innovation over a period of time. In terms of cell formats for batteries, so there are like mostly three types of cells at the moment available in the market: a cylindrical cell, a prismatic cell, and a pouch cell. So these are three kind of cells you'll see in the market. So each design balances energy density, mechanical robustness, and thermal management. So for example, a cylindrical cell, the bigger ones that are being manufactured in the gigafactories of Tesla recently are being used as a structural support for their cars so that they get rid of the extra metals that are needed for uh, and it forms a bed of the car itself. So because a cylinder cell can hold on the weight much higher, they kind of used polymers to bond between these cylindrical cells to create a more rigid structure which is torsionally stiff and also supports higher weight. However, BYD has gone for this blade kind of batteries, but using a vertical stacking method, they also able to achieve cell to structure design, which kind of becomes a load bearing structure within the bed of the vehicle. Um, if you look at the past issues, the major issues with the batteries, I would give an example as the Samsung Galaxy Note 7 recall in 2016, which underscores the importance of the design, the quality control, and thermal management. The poorly manufactured separator was the one which caused the short circuit and the thermal rundown, where you must have noticed a number of news giving out how the Galaxy Note 7 caught fire while on the pocket. And that's when the market paid more attention to the separator chemistry, and there have been consistently a number of innovations and developments since within the last few years. The Tesla's unique choice of the cylindrical 2170 cell for the Model 3 and the 4680 dimension cell for the newer models. The numbers are nothing but the diameter and the length of the battery. It's a combination of that in millimeters. Um, it kind of helps in a uniform thermal distribution, and also it helps in the structural integration, as I mentioned before. And they also did a newer innovation whereby they eliminated a copper strip conductor for charging, which historically the design used to be a single piece of copper strip, which causes all the electrical charge to be focused on a smaller piece of the entire battery pack, which also cost lower charging cycles. However, with the newer innovation, uh, they made a copper strip slits throughout the batteries edges, and they formed a unique pattern so that the entire charge goes through the all the surface of the battery at the same time. This increases the charging time, which also helps in overall reducing the time it takes to charge a full battery pack of a vehicle. Um, in terms of the second life applications, EV batteries degrade to around 70 to 80 percentage of the original capacity. They can be repurposed for stationary storage, extending their useful life and reducing waste. So in terms of waste processing of batteries is much more efficient that A battery could last much longer nowadays than the actual before the car breaks down. So the batteries that are recovered are not necessarily straight away being recycled, but they can be repurposed as a stationary storage to still use the remaining capacity it has got to offer. So lithium ion technology is still remains as a foundation for all the batteries, but rather than drastical changes in the battery technology, there has been incremental improvements over a period of time in terms of new electrode materials, advanced electrolytes, and improved safety mechanism that continue to push the performance envelope. So let's speak quickly about the next chemistry in battery, which is becoming a very big breakthrough in the entire battery chemistry, and it's slowly getting commercialized. So if you compare typical sodium ion battery, which is what is the neo technology, with the lithium ion, you can see the energy density is in par, which is around 170 to 775 to 200 watt hour per kilogram, whereas the lithium ion is 150 to 260. However, you can see the charging cycles is much higher compared to lithium ion, around 4,000 to 5,000 cycles. And most importantly, the cost of the sodium ion is projected to be much lower than a lithium ion in the near future, as soon as the economic scales hit in. And another important breakthrough in the sodium ion technology is the charging time. Uh, it is much lower than the lithium ion. Around 80% of the battery gets charged within 15 minutes. Um, in terms of the materials that are used in sodium ion technology, chemistry, Prussian white, manganese or iron, and an aluminum conductor are used compared to a nickel, cobalt, graphite, copper conductors used in lithium ion. So what are the benefits of a sodium ion? So the sodium is quite abundant compared to nickel and cobalt. Um, the wide operating temperature. So, as you know, the lithium ion chemistry packs that are currently used in electric vehicles, it has to operate within a normalized temperature range. So, too cold or too hot of temperature is not acceptable for current chemistries. That's why you have battery management system or temperature management systems. However, the sodium ion chemistry can operate in much lower temperature as well as much higher temperatures. So this means that you don't need that extra thermal management systems to be integrated into your car, which also lowers the cost of the car over a period of time. The anode chemistry or electrolyte is much safer compared to lithium ion. So this particular sodium ion is emerging as a promising and is complementing to the lithium ion technology. This is currently particularly of a big interest in terms of grid storage and low cost electric vehicles. So as I mentioned before, sodium is abundant and widely distributed, and there's no supply chain issues or constraints. So sodium is not geographically constrained to fewer countries. It's kind of available everywhere. The modern sodium ion cells achieve energy densities, as I told you before, is much higher, whereas the research cells are exceeding 190 watt hour. So fast charging is one of the key selling points of sodium ion batteries, and also the temperature range, as I mentioned before. Um, so the costs are slightly higher. However, mass production, once it hits that level of economic scales currently being put out by lithium ion, the overall cost per kilowatt hour will drop in the near future. In terms of the cathodes of sodium-ion batteries. It used layered oxides, uh, polyanionic compounds, and Prussian blue analogs, which avoids nickel and cobalt. As I mentioned before, nickel and cobalt are predominantly deposited within Democratic Republic of Congo, and it's one of the highest cost in terms of the battery chemistry. So, so researchers are trying to find ways to get reduce the overall usage of nickel and cobalt in their battery chemistry, and sodium ion is proving to be such a good alternative for that kind of approach. Um, so CATL, in terms of commercial examples, the CATL company has delivered a first generation sodium ion battery back in 2023, and it plans to combine sodium ion and lithium ion cells in the same pack for EVs, so that you have a portion of the kilowatt of the battery pack provided by lithium ion for quick charging and higher density, whereas a higher portion of the battery pack is used for sodium ion for lower discharge and quick charging as well. Chinese automaker JAC introduced a EV with sodium ion battery from HINA battery. And currently in India, Reliance is building a sodium ion production capacity. Sodium ions are larger than lithium ions, making it harder to find stable host structures. Graphite is unsuitable for sodium ion anodes. So hard carbon derived from biomass or synthetic precursors is used. The research currently is focusing on improving cycle life and increasing energy density by optimizing cathode materials and electrolyte formulations. Um, the sodium-ion battery cells may not completely replace lithium-ion in high-energy applications such as long-range EVs or aviation. However, they offer a cost-effective solutions for stationary storage and short-range mobility. Sodium and aluminum both are abundant, and sodium-ion batteries could help democratize energy storage and reduce dependence on geopolitical sensitive materials like nickel and cobalt. So let's discuss a little bit more about advanced cathodes and anodes that are around the corner. This particular slide explores the innovations that push the boundaries of lithium-ion performance. Um, in this particular one, the LMFP, lithium manganese iron phosphate cathodes, um, build on the lithium iron phosphate chemistry by substituting some iron with manganese. This increases the operating voltage and thus the energy density by 15 to 20%, reaching up to 230 watt hour per kilogram. LMFP remains cobalt free. As I told you before, cobalt is geopolitically a material which they're trying to reduce in the overall chemistry, and retains the safety and long cycle life of LFP. However, it suffers from lower power capability and manganese dissolution, which can reduce the cycle life compared to lithium ion. So researchers are currently working in developing coatings and dopants and electrolyte additives to mitigate the aforementioned issues. Against Chinese cell maker CATL, BYD, Eve Energy, and Gotian are planning to mass produce LMFP cells, and specifically Gotian's L600 Astroino battery, which was announced in 2024, claims 1,000 kilometer range in a compact EV. So if you assume that if such a battery gets mass produced, due to economics of scale, the cost will reduce, and a compact EV with that 1,000 kilometer range would be much cheaper than the current offerings. On the anode side, silicon offers a theoretical capacity of 10 times that of a graphite, which is currently being used, which is around 3,600 milliamp hour per gram versus 372 milliamp hour per gram. So this increases the density much higher compared to what is being used with the graphite at the moment. Silicon, however, expands dramatically during lithiation, causing mechanical stress and capacity fading. So during this process of lithiation, which is during the charging and discharging, while using the silicon as an anode, it would expand and contract, which kind of puts a mechanical stress to the battery cell. And researchers are currently working to mitigate this, and they are actively trying to innovate to get away from this particular issue. Companies like Sila Nanotechnologies and Group 14 are developing silicon carbon composite anodes that use nanostructured silicon to accommodate expansion. So that the nanostructured silicones within the carbon atoms, it would limit the amount of expansion, and in terms, it would reduce the stress it causes due to mechanical expansion. Over the time, these materials could reduce the anode cost share to 2% and increase cell density by 20 to 40%. Um, Partial replacement of graphite, around 5 to 15% of silicon, which is currently being looked at, uh, and that's been classed by researchers as maintaining the mechanical stability, while high silicon anodes use conductive binders and flexible matrices. So different percentage of silicon is being tried for different applications of the batteries, and that's been actively being researched on at the moment. Pre-lithiation techniques add lithium to the anode to offset the initial loss of the lithium due to the formation of solid electrolyte interface, boosting the capacity. Nickel-rich single crystal NMC, cobalt-free high manganese cathodes, and high voltage spinels are some of the other advancements in the cathodes. So with these advancements, um, with these innovations, the diversity of material research aims at boosting the energy density, reducing the cost, and limiting reliance on scarce metals. So all these research are happening overall, which if we list down the constraints of a modern commercial battery, a size and weight, charging cycle, uh, the energy density, the temperature where the range of temperature it can operate on, um, and how quick it can charge and discharge, and the cost per kilowatt. So these are the key commercial elements that are being explored, and the sweet spot of there's no one battery chemistry that can hit all these points. Depending on the applications, there's a varied set of chemistries that are being developed, which can be formulated for various applications. So let's dive a little bit about solid state and lithium metal innovations. So solid state batteries is a very upcoming and interesting technology, and it's not commercial yet. However, a lot of money is being poured into this research at the moment. Um, the main agenda in terms of the research into the solid state and lithium metal innovation is to uh, prevent is to make a very safe battery, so that even if you put a nail through the battery, it will not catch fire, and it's completely inflammable, and it is not flammable, and it's much safer compared to the existing lithium-ion chemistries. So what it does basically is it replaces the flammable liquid electrolyte that's been used in most of the batteries that we have at the moment, including the one in our phones, and the separator. So it replaces the liquid electrolyte and the separator with a solid electrolyte, uh, which enables the use of lithium metal anode. Um, this promises very higher energy density, improved safety, and faster charging. So who is pioneering this? So Factorial Energy's solid state technology, which is also called FEST. They have cells which use a quasi-solid polymer ceramic electrolyte. It's a quasi-solid polymer ceramic electrolyte, and have achieved energy densities of about 375 watt hour per kilogram. They can charge from 15% to 90% in just 18 minutes, and operate at a temperature between minus 30 degrees to plus 45 degrees. Wide range of temperature it hits, and also it charges much faster. The Stellantis plants, Stellantis is the OEM which manufactures a number of car brands, from Renault to Nissan to number of car brands. It integrates these cells into the demonstration fleet by 2026. So solid state battery is pursued by a number of commercial car brands and other commercial companies as one of the major breakthrough battery technology in the near future. University of California, San Diego researchers developed a lithium aluminum alloy anode that allows lithium ions to diffuse up to 10 billion times faster by controlling the beta phase within the alloy. So their solid state cells maintain high capacity over 2000 cycles, demonstrating the potential for long-lived lithium metal batteries. So this is another selling point when you have more thousands of cycles of a battery, which means it would outlive a typical application of electronic or electrical device, including the electrical cars. Compared to the other components, the battery live longer, so it could be easily harvested for further use later on. The types of solid electrolytes that are being used is sulfide based, like high ionic conductivity but sensitive to air, oxide based, which is stable but brittle, polymer based, which are flexible but lower conductivity. So these are some of the challenges which are the researchers are going through at the moment. Um, I mean, like that, the challenges are mostly about interfacial resistance, dendrite penetration. As I mentioned before, dendrite are like micro cracks within the separators, and the manufacturing scalability. So they have achieved certain chemistries which kind of fixes this problem. However, they may not be able to scale it up in a commercial basis. The Toyota's prototype solid battery, as I want to mention specifically about Toyota. So Toyota is pushing very hard and investing quite a lot of money in pursuing the solid state chemistry. And, and they have some prototype solid state cells, and they're targeting commercialization by uh, like 2030, around that time. And another company which I want to mention in solid state chemistry is QuantumScape, which is been listed in New York Stock Exchange, and they are pioneering in solid ceramic electrolyte development. And Solid Power is another company which efforts to combine sulfide electrolytes with silicon anodes. So these are three companies, Toyota, QuantumScape, and Solid Power, which I want to mention, that they are pursuing very strongly on this solid state electrolyte based chemistry for future batteries. Apart from solid state, high apart from solid state, lithium
So
metal
Joe
innovations like anode-free cells, where lithium is plated directly onto the current collector during charging, and protective coating that suppresses dendrites. So these developments aims to deliver 500 to 600 watt hour per kilogram energy density, double that of today's lithium-ion cells. Just think about it. You have half the battery size, but giving the same range in an electric vehicle. Also, a sweet spot of around or exceeding 700 watt hour per kilogram would be a sweet spot when it can be useful for avionics, for example, to run a battery-based light aircrafts. While solid-state batteries remain several years from mass production, might be like 5 to 10 years, they are the frontier in high energy, safe energy storage in the near future. So there are some high energy batteries which are being pursued as well. So one is a lithium sulfur, the other one is a lithium air. So what is special about lithium sulfur is light and abundant. Sulfur is available everywhere. The cost is around 60 US dollars per kilowatt hour. The energy density is much higher. However, the cycles are less than 50. Um, Platinum nanoparticles stabilizes the cathode. 92% capacity retains after 500 cycles. So these are currently under development or under research. Whereas the lithium air, if you look at it, solid composite electrolyte enables four electron reactions. Lithium so dilithium oxide formation, and it delivers up to 1,200 watt hour per kilograms, much higher, about 4 times that of what we currently use in our electric vehicles. The rechargeable time is more than 1,000 cycles at room temperature, and solid electrolyte and catalyst eliminate the flammability concern. So lithium ion is another chemistry which is pursued for avionics in the near future, which it could be used for light aircrafts where high energy density and lower weight is much critical for such kind of applications. However, they do suffer from certain issues of um, like air oxide formations and some other issues which are currently being researched in terms of how to get it commercialized. So let's look at quickly what other applications that are currently being pursued, which is very key, and what kind of chemistry being used for such applications. One of the main, other than electric vehicles and backup batteries, grid level storage is something which is being pursued by a number of governments, countries around the world to stabilize their grid while the demand is high and the supply is low, or when the supply is much higher and the demand is low and they want to store the excess energy somewhere. Historically, as I told you before, coal and gas power plants has been used, which were never being turned off. Like they've been put on hold, which costs a lot of money to maintain. And as soon as if there is a grid optimization has to happen, they come online to just optimize the grid and they go offline, which is much higher cost and also environmentally degrading. So battery grid scale storage batteries are currently being pursued in terms of as an alternative for coal and gas power plant in the longer run. So in that, vanadium redox flow batteries, which offer a long life, minimum degradation, and high safety, the US Department of Energy is invested quite like $500 million into research into that. Iron Air Batteries, which is developed by Form Energy, a US startup, and uses iron, water, and air, no thermal runaways, It provides 100-hour duration, and the first commercial deployments are currently underway. Liquid metal batteries like molten CASP or calcium antimony, it promises lower cost around 180 to 250 per kilowatt hour today, and it's projected to cost much lower, like 21 US dollars by 2030, and much longer lifespan. So these kind of technologies, which would definitely be a game changer in terms of providing an alternative uh, to normalize the grid in the future, and can work alongside uh, 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 renewable energy like offshore wind turbine, solar, and nuclear technology, modular nuclear technologies, to store the excess energy when the demand is much lower. In terms of supply and demand, the lithium demand grew nearly 30% in 2024, nickel, cobalt, and graphite by around 6 to 8%. Energy applications account for around 85% of demand growth, and prices dropped due to supply expansion. So the top three refining nations produced 86% of refined minerals, and the top three mining nations supply 73% of critical ores. So you can see that the current critical minerals are highly concentrated in few countries, which kind of uh, reduces the democratization of these critical minerals, just like oil at the moment. However, more countries, or the research is pursuing in such a way that we don't repeat the history of oil, where it's been focused on OPEC plus nations. Likewise, you have fewer nations controlling vast majority of these critical minerals, and the technological breakthrough should democratize such that more countries have got local supply chain rather than depending on other countries, which could cause geopolitical tensions. In terms of mining, there's been a lot of technological breakthrough and innovations happening. In that, I have to know the most notable one is called direct lithium extraction, DLE, and it recovers 80 to 90% of the lithium from the brine solution, compared to 30 to 50% from the traditional evaporation. So they just pump out the brine historically, and just like how you extract salt for your table salt out of seawater, they just extract out of the lithium brine solution. However, this direct lithium extraction doesn't use that kind of method. It reduces the water usage overall, but it requires higher capital for the miners in terms of recovering 80 to 90% of the lithium. So these are capital investments that are currently ongoing. Uh, so over a longer run, when once the capitals are recouped, the cost of mining will drop drastically for lithium, which will in turn bring down the cost of lithium as well in the long run. So China controls around 80% of rare earth processing at the moment, 60% of cobalt and lithium refining. So even the cobalt is mined in Democratic Republic of Congo, the processing or the refining, 60% of them is happening in China. Likewise, the lithium as well the same. The Democratic Republic of Congo produces 70% of the global cobalt, often via artisanal mining. So in total, the sub-Saharan African region holds around 80% of manganese reserves, and new lithium deposits are emerging in Mali, Guinea, and DR Congo. The lithium triangle, also is Argentina, Bolivia, and Chile, contains roughly 60% of the global lithium reserves. Brine extraction there uses 500,000 to 750,000 liters of water per ton of lithium. So current method is very damaging in terms of water usage and for environment. So more capital is required in the future for this DLE method of lithium extraction. So Canada and US are investing billions in domestic mining and processing. Canada lists 31 critical minerals, and the US aims to cut permitting times to 3 to 5 years. So all these are happening in parallel. So we would see a demographic shift in terms of mining and the refining in probably the next 5 to 10 years. There are geopolitical issues in terms of critical mineral supply as of today, as I told you before, like probably in 5 to 10 years, this could change. The resource nationalization is rising. So, as I told you, like more and more countries don't want to get trapped in the older era of fossil fuels, where fewer countries control the price of the oil. Likewise, they don't want the critical minerals to be held up by fewer countries, which would be controlling the price in the longer run. So export bans on nickel by Indonesia, cobalt by Congo, and rare earth by China aim to capture more value domestically. So China dominates processing and refining, giving it leverage over supply chain. Nations respond with friendshoring and alliance building. The US, Canada, and the EU are investing billions to reshore processing, sign strategic partnerships, and create stockpiles. Uh, Geopolitics shape price, trade policies, and technology choices, which is stable, diversified supply in essential for critical climate goals. However, there's one big difference between the era of fossil fuel and the era of critical minerals for battery technology is that battery uh, is never the materials that goes into the battery is never lost. As I told you before, as the cycles of the battery increases over a period of time, the the other components of a particular application runs down or breaks down before the usable cycles of the battery runs out, which means the batteries could be harvested for reuse. And even at the end of the cycle of batteries, the materials can be recycled to make newer batteries, which cannot be done on fossil fuels at the moment, even though carbon capture technologies are getting developed. But that's one main difference between the battery technologies and the fossil fuels of the last era. Supply chain vulnerabilities. So China processes over 60% of the cobalt, lithium, and manganese, and extracts more than 70% of the natural graphite. Export restrictions. So China's December 2024 rare earth ban due to the trade tensions between China and the US, and also the Democratic Republic of Congo, cobalt export ban on February 2025, Indonesia's nickel ore ban. So these kind of uh, caused by geopolitical issues. However, it would disrupt the supply chain and make the supply chain much vulnerable, which in turn impact the overall production capacity and the scaling up of the batteries much faster, which in turn impact the climate goal, achieving the climate goals globally. So US resources alone is insufficient for EV mineral demands. So diversification through alliances is definitely essential, and diversifying processing is costly. Industrial policy and international cooperations are required. So, what is India doing in all this? So, from Indian standpoint, so let me quickly explain about grid storage in the Indian standpoint. India is investing in large-scale battery energy storage systems to stabilize its renewable energy grid, which is happening at the moment. And also, Indian government has auctioned for several gigawatt hours of battery storage and pumped hydro projects under the National Mission on Advanced Chemistry Cell Battery Storage technology, which is illustrate the commitment that India is uh, uh, showing towards large-scale battery storage. In terms of critical minerals, demand and supply, India recently discovered a significant lithium deposit in Jammu and Kashmir, but still relies heavily on imports for lithium, cobalt, and nickel at the moment. State-owned companies such as Carney's Baidesh India Limited is forming joint ventures in Argentina, Australia, and Africa to secure critical mineral supplies for domestic industry. So India is actively working to secure the supply chain to increase the battery production within Indian borders. So in terms of mining breakthroughs, we can see that uh, domestic exploration includes initiatives to extract lithium from brine in Gujarat's Rann of Kutch and hard rock in Karnataka's Mandya district. Indian research institutes are examining direct lithium extraction and sustainable mining technologies tailored to local geology. So India aims to reduce dependence on China for battery cells by offering production-linked incentives to encourage local manufacturing. Diplomatic agreements with Australia, Bolivia, and African nations seeks to diversify supply of lithium and rare earths, while geopolitical tensions highlight the need for secure and resilient supply chains. Mining projects in India must balance resource extraction with the rights of tribal communities and biodiversity conservation. The proposed lithium mine in Jammu and Kashmir will require a careful water management strategy and environmental safeguards to protect fragile Himalayan ecosystem. So that's one of the reasons, even though a large deposits of lithium is found in Jammu and Kashmir, it's not pursued very hard quickly to safeguard the Himalayan ecosystem and also to carefully manage the water resources over there. So in terms of the environmental and social impact, 16% of critical mineral sites are in high or extremely high water stress regions. Lithium brine extraction uses up to 500,000 gallons of brine per ton. Atacama mining consumes over 65% of local water. Water depletion and contamination threatens indigenous communities in Chile and Argentina. Similar risks of cobalt in Congo and graphite in China will exist in terms of environmental social impacts. Ethical concerns include child labor and unsafe working conditions do exist in Congo. Innovations like direct lithium extractions and microbial treatment can reduce water usage and pollution. However, the capital investments are quite huge and it may not be realized in next few years. In terms of policies and regulation landscape, the extraction target, if you look at the European Union, is around 10% by 2030. And United States, it wants to boost the domestic mining via sections 232 orders. Processing targets around 40% by 2030. And US is investing in refining capacity, tariffs on Chinese graphite and copper. So they're using kind of tariffs to increase the refining within the above boundaries. And the recycling target is around 25% of demand. Recovery should be more than 95% of cobalt, nickel, and copper, and 80% for lithium in European Union. And US is aiming to recover 90% by recall and price competitions. And digital passport has become a mandatory by 2027 using QR codes in European Union and is being under discussion in the United States at the moment. In India, India's battery waste management rules 2022 imposes extended producer responsibility on manufacturing and importers, mandating collection and recycling of spent batteries. Uh, so Redwood's process recovers more than 90% of lithium, cobalt, nickel, and copper, 80% less energy, 70% lower CO2, and 80% less water versus mining. So these are ways of creating a circular economy so that recycling, as I mentioned before, would save water and the resources and the energy compared to how we used to do it in fossil fuel. So this is one of the bigger differentiator between utilizing fossil fuel and the battery technology of the future. So how does the future look? Demand would continue to climb until we replace most of the fleet of the current ICE combustion engine vehicles in the world, and potential deficits for lithium and copper would occur by 2030, despite the current surpluses. So because of the increase in capacity in the battery production. In terms of research directions, sodium ion is going to be highly scalable in the near future. LMFP, lithium manganese iron phosphate, is going to is the stability of that is going to increase. Solid state battery manufacturing is going to happen. From research is going to go into commercial production. Lithium sulfur and lithium air battery cycle life would improve drastically, and lithium, as I mentioned before, lithium air batteries would innovation and commercialization of lithium air batteries would eventually will help in replacing our avionics fleet and to decarbonize our aeroplane sector. In terms of grid integration, long duration storage technologies complement short duration lithium ion systems. And in terms of digital innovations, battery passports, AI enabled sorting and predictive maintenance will enhance transparency and efficiency. Sustainable sourcing and circular design will address water, biodiversity, and human rights issues. So just to conclude, batteries underpin the clean energy transition. Advances in materials will unlock new possibilities. Supply chains remain highly concentrated and environmentally intensive at the moment. Diversification and sustainability are paramount for the near future. And policies and circular economy initiatives will shape future markets and foster innovation. Um, The current research students have a vital role in exploring the next generation chemistries, improving the recyclability, and protecting communities. So this whole transition over the next decade is very paramount in terms of decarbonizing the world, achieving the climate target of the COP directive, and having a very sustainable energy storage technology for the future, where renewable energy is going to replace most of the fossil fuel energy of the world, capacities of the world. And that's it, really. Any questions? I'll just open the floor for questions around this.
Thank you, sir.
Thank you.
Dear participants, it's your turn to ask questions related to this topic or our session, and you may post the questions on your chat box. So we have a question on the chat box.
All right, okay.
Why lithium-ion batteries 100% charging is not allowed?
Yeah, so as per the current chemistry of lithium ion that's been used with the cobalt and nickel, um, the sweet spot of lithium chemistry, where the the reduction of dendrite formation and the expansion and the thermal management issues uh, would not occur if the charging capacity is less than 20%, or sorry, if it is more than 20% or less than 80%. So as of current chemistry that you use in your mobile phones or laptops or electric vehicles, the sweet spot to have extended battery life is between 20% and 80%. So what happens if you go beyond that 80% means there's thermal changes that happen within the battery, and there are minute expansions and contraction which causes a mechanical stress, and that reduces your overall lifetime of the of your battery. That's as of today's battery chemistry. However, as we discussed before, the future chemistries would overcome all this, and you wouldn't have to be so constrained about thermal runaways or mechanical stresses. So industry would adopt accordingly. So, in terms of data analytics and AI, so as far as what I have noticed, AI and machine learning are currently used in two areas. One is during the battery testing phase, where there is something called yield per kilowatt hour. So, not all the batteries that are created in the factories make to the production. There's a percentage of batteries that goes bad, and they do intensive testing. They used to do batch testing in the past, which kind of reduces the time it takes to production. However, there's a continuous life cycle testing method which is being introduced by Tesla recently in their cylindrical battery, where learning is used while the batteries are formed to continuously test by charging and discharging, and it seems that the yield is increasing and the wastage is reducing per kilowatt hour because of the machine learning usage in the testing area, which is a quality assessment. And another area where the AI and data analytics are used are two places. One is in your battery thermal management in your latest electric vehicles, where it automatically, when you plug in your charger, it automatically detects and preconditions your battery's temperature before it starts the charging and it discharges charging. So one such technology which I can give as an example where AI is used. So there is a utility company called Octopus in UK. So what they are doing is they are providing a specific EV based tariff. So unlike in India, there are more electrical companies in UK. So you have to choose, like how you go into a mobile contract, you have to choose your contract for a period of time with your electrical company. And this Octopus Energy, what they're doing is they remotely take control of the charging cycle of your electric vehicle's battery. It automatically they speak to your battery from their cloud AI, and they find out the cheapest time of the day when the electricity is cheaper, where like more supply is happening and less demand, and that time they automatically speak to your car and they start charging your car. So that's something where sometimes, like, that's an area where AI is and data analytics are heavily used, where they used to figure out what is the current demand in the grid. It's called something called smart grid, and the supply that's been excessive supply that is generated, and they work out the batteries that are hooked up at that point of time, and the excess energy is getting deposited into the battery so that uh, the energy producers have some place to deposit their energy, and also
गेली ती लिंक
electricity
पहिलंच ती
consumers would have cheaper tariffs to consume the energy.
तितक्या नालायक असतं ना
I hope I answered all the questions.
आता याच्यात काय होतं इथं साइन इन म्हणायचं सिम्पल आहे इथं जायचं फक्त बस मला हे सांगते ना मग तू
Thank you, sir.
Thank you.
Behalf of the organizing committee and all the participants of the FDP, I extend my sincere gratitude to our distinguished resource person, Mr. Dev Kala. Sir, your talk has enriched our understanding about this session and for delivering an exceptionally informative and insightful talk on the battery technologies and critical minerals. Provided immense value to all participants. Once again, thank you, sir, for your esteemed presence and for sharing your vast knowledge with us. Thank you, sir.
Thank you very much. Thanks for inviting. Thank you.
Dear participants, please fill your feedbacks for the session. The feedback link is already shared in the chat box. Now it's time to start our next session. For this, I invite Dr. Glan Devdas. It's a privilege to introduce Professor Dr. Glan Devdas ji, a distinguished academician with over 2 decades of experience in teaching, research and academic leadership. He is currently serving at CMR University, Bangalore as a professor and director of the Directorate of Research and Innovation. He has played a key role in fostering strong research and innovation culture, promoting educational technology, entrepreneurship and quality research practices. With an impressive record of over 60 research publications and guidance of numerous UG, PG and PhD scholars, his contributions span control systems, intelligent computing, and instrumentation engineering. He is also actively involved in organizing conferences and building global academic collaborations. We are honored to have such an experienced and visionary academician with us today. Please join me warmly welcoming Professor Dr. Glan Devdas. Once again, welcome, sir. Welcome to the session.
Thank you, ma'am. Thank you for your nice introduction. And good afternoon to all my dear participants. Today, is it audible?
Yes, sir.
Yeah, okay. Okay, the screen sharing is enabled to me.
Naina, you have to make the Glancer as co-host.
I'm co-host or not?
Sir, just a minute, sir.
Okay.
Yes, sir. Now you can proceed.
Okay, sir.
Sir, hope you will be able to share your screen.
Yes, sir. Yes, sir. Just a minute. I am taking my. Okay, is it visible?
Yes, sir. Please make it full screen, sir.
Now it's okay.
Yes, sir. Okay, sir.
Okay, so good afternoon to you all, and once again I thank for the opportunity given to address in this ATAL FDP, and the topic is advanced functional materials and rare earths for next generation sensors and IoT applications. Okay, so first we have to start from this. What is Internet of Things, and what is the role of the sensors there, and how rare earth materials are going to be utilized to create a best sensors for this applications, day-to-day applications. So what is IoT? Nowadays in the after Industry 4.0, we are very much aware about the term IoT, Internet of Things. Okay, day to day in our daily life, we are using this IoT. even in our home and home automation systems, in our bedroom, in our air conditioned system, in our laboratories, and always we are making this internet of and things with us. So what is things? Things may be an object, things may be an process, things may be an a home appliance. So all the things can be. Before that, before this concept, we should know what is the difference between the smart and intelligence. These two terms are nowadays everywhere we are using. Even we are applying for some conferences, there is a term that that intelligent computing and intelligent sensors, intelligent communications, smart. What is smart and what is intelligent? When we are calling a certain person at a smart and intelligent, that is very important. So without that knowledge, we cannot go with that Internet of Things. Internet of Things is not my whole thing, whole concept of what I am going to tell here. Okay, just I am going to give a brief introduction of that. Okay, how this sensors can be used. Okay, so intelligence and the smart. What's the phrase or colloquially how we can differentiate these two? Okay, now in our daily day-to-day life, some persons, when we are calling it as a smart action, okay, or smart decisions, and when we are calling someone as an intelligent, these two are very much close, and a slight difference between these two. Okay, so any answers from audience side or participant side? What's the difference between smart and intelligent? Anyone? No, I couldn't see that in the chat box anything you are posting. Just go and unmute your mic and interact if you want, or else I will tell you what's the difference between smart and intelligent. Okay, smart means if someone has self-diagnosis capacity or self-calibrative capacity. What is the difference between the self-diagnosis and self-calibration? Okay, for example, I am having some disease in my body. Okay, I am able to find out what is that. So some headache or some fever or something, some symptoms. Using those symptoms, I can able to identify that, okay, I am suffering from this one or some particular case. Okay, so that is self diagnosis. Okay, if I mission that can able to diagnose itself, okay, what is its fault? Okay, what happened it? Because of the sound variation, because of the noise variation, because of some parameters variation, it is able to find that, okay, some issues are there. That is a self diagnosis we are calling. Okay, so self diagnosis capacity is injected into a system. The system cannot have the self diagnosis unless otherwise the intelligence is injected in it. Okay, so then we are calling it as an smart systems. Okay, self calibration, self diagnosis comes from the self calibration. What's the term calibration means? Calibration is always comparison with the standard. Okay, you can compare some of you with the film stars or with the knowledgeable person or some Einstein or Tesla. Okay, I can compare one person with other person, or in the researcher you can compare. Oh, he is having this much of citation. I want to get that much of citation, that much of H index. All these things are that is the calibrations. That is I'm comparing and correct myself. How to become that? Okay, so I'm finding the error, finding the gap, and filling the gap. That's called the your calibrations. So if an equipment or a system or a sensor has these capacities, then we are calling it as a smart sensor, smart system, or whatever may be the smart person also. Okay, without self diagnosis and self calibration, no one can act as a smart one. Okay, so what is an intelligent then? So intelligent has all the smartness with that, but it has a communicative capacity. It has able to communicate. So I am having all knowledge with me, but I can't able to communicate. How the external world come to know about me? How what's the visibility there? Okay, so there is no visibility. So if a sensor can able to communicate with other sensor, then we are calling it as an intelligent. So for making intelligent, smartness is required. Okay, it is one step ahead, that intelligence. So here that one equipment is going to communicate to other equipment. That is what, through the medium of the internet. Okay, so things are going to communicate, things are going to calibrate themselves, things are going to diagnosis, and things are going to obey your order. Then we are calling it as it is an internet of things. So internet of things, any device, anybody, anywhere, any business, any network, at any time. Okay, so they are going to interlinked each other. Okay, interlinked each other. So I am sitting from here and viewing what is happening in my house by means of the camera, that is the smart cameras that what I have installed in my house. Okay, so I am communicating from here to that of my house. Then that is called the internet of things. So it is linked by means of the internet. Okay, so any device, anybody, anywhere, any business, any network, and anytime. Okay, so all these things are going to be interlinked or interconnected. What is required? The required thing is data. Without data, nothing you can do. So how the data can be captured, how the data is going to be transferred, how the data is going to be processed, all the things are there in the internet of things. So if you are taking your research domain as an IoT, you can do all the works like your data analysis, sensor networking, and the control. Everything will be included in your IoT. Okay, so for that some platforms are required, and if you are trained in that platform, then the data analysis is required, then networking is required. So one by one all the domains. So it is a very good interdisciplinary and transdisciplinary area. Anybody can involve their research in that case of the internet of things. Okay, so the fundamental thing of this internet of thing is the sensors. Okay, so today our class we are going to see how these sensors are used or fabricated. I am not going in depth of the fabrication technology of the sensors. Okay, but initially I told you that about the smart sensors. So smart sensors means what? The self diagnosis, self calibration, all the capacities are required. Okay, so before that we should know what is sensor. Okay, what is sensor? So from the sensor, since sensing only you can collect the data. Without sensing, the data will not be collected. So that's what the sensor, important of the sensor is required here. Okay, so anyway, yeah, before that we will see the application of the IoT in every places, like your smart lighting, smart intelligent appliance, and instruction detection, smoke, gas detection. So wherever the detector is there, that is nothing but other name of the sensor. Okay, so I am detecting means sensing. Without sensing there is no nothing, detection will takes place. Okay, so that is smart parking, smart roads. So knowingly or unknowingly we are using IoT in our day-to-day life. Okay, all the things we are using. So weather monitoring, air pollution monitoring, noise pollution monitoring, all things comes under your environmental and energy, like who are all doing their green energy projects, or that is solar energy projects, renewable energy projects. They are using the IoTs, and that is smart grids you are using, and your even your management also. Nowadays lot of management people, they are doing their research in the IoT area. Okay, like the smart payment, smart vending machines, and logistics, like your route generation. And if in your EV also, now you can find the optimization, optimum path, or your unmanned vehicles, you can use this, as well as there's fleet tracking, shipment monitoring, remote vehicle diagnosis, smart irrigations in the agriculture. It is used in many places, like, okay, monitoring the crops, okay, and greenhouse control, smart irrigations, and in the industry, manufacturing industries, like industry 4.0 and 5.0 also nowadays it is coming. So machine diagnosis, and when the fault diagnosis, indoor air quality monitoring, health fitness monitoring, wearable electronics in the biomedical area. So every places the IoT plays an important role. And the next generation, the IoT is going to dominate, since now everywhere we are going to incorporate this AI here. This AI is going to give much more intelligence in that of the system. Okay, so sensor, we know what is sensor. Everybody knows. In the school level, they taught you about the sensing organs. Okay, how many sensing organs you are having, and what are the sensing organs, you know. Okay, so without sensing, nothing will happen. At least I have your vision, your hearings, and your smelling, touching everywhere. This sensing is will have taste as well as. Okay, similarly, when some device, that is how this sensing happen. Sensing happen means what? Some stimulations have happened, because of that some signal is generated. Okay, so generation of the signal is nothing but sensing. Okay, so what actually some good fragrance smell is coming from the kitchen. Okay, your wife or your mom is okay today cooking chicken, means your sensing organ is okay sensing that some chicken is cooking there. Okay, at the lunch I want to go and to take a tasty food, and your brain is now that what it creates some signals, and automatically you are going to that the hungry or not, you want to taste it, isn't it? So this is the case of the sensing. And some good music you are hearing, okay, automatically your brain creates some signals based on this one. So some signals should be created. The outcome of the sensing is the signal. Otherwise, in the normal day-to-day life, or the modern life, we are calling it as a modern technology life, we are calling it as a data. Okay, some data is now generated by means of the sensing. So outcome of the sensor thing is the data. So sensor is a input device or output device? Anybody is there, please you can respond, no? Otherwise it one way traffic. Sensor is a input device or output device? Anyone is responding? Organizers all are there, or is it audible?
Yes, sir.
Okay, then why nobody is responding? That's what. Okay, my question is, sensor is an input device or output device?
Is it input device?
Okay, good. At least organizers are answering. Okay, good. Okay, so this is an input device. Wherever we are going, the sensor is an input device, and your actuator is the output device. That is how actuator is going to manipulate something, or from the sensor. It is sensor is always generating the signal and give to the controller. Controller is giving it the command to command, and the command is action by means of the actuator. So because of that, some action is takes place. So that the main part of the sensor in industry is the control applications. That we will see it later. Okay, if time permits. So why this is an common topic to all. Why I choose this one is, it is very common, and there is no need of the engineering knowledge or anything is required. Day to day you are using, okay, and in your daily life you are using. In your mobile phone there is a lot of sensors. That also I will touch what are the sensors available, basic sensors available in the mobile phone. Okay, and nothing you are going to lose by knowing these things, even you are in any domain. Okay, even you are in from the literature also, it will be useful, since you can teach your kids also for about the sensors and other things. Okay, so basic definition is a device that measures a signal and process the data from the signal for real-time monitoring of the variety of the parameters. Okay, so different devices are there. These are all called, we are calling it devices. Okay, so devices used for different measurements, and the outcome of the sensor is a signal. Okay, so what do you mean by signal? Signal means we are not calling everything as a signal, and some information should be there. Okay, so signal carries of some informations. It is a physical, anything, any quantity, it has some information, then we are calling it as a signal. Okay, so I am stop I should stop by when red light is glowing when I'm riding my bike. Okay, in the traffic signal. Okay, that indicates that some information. So information is coming, that's what I am calling it as a signal. The information is what you have to stop there when the now red light is glowing. Okay. When green light is glowing, you have to go. That is a signal. So without information, some light is glowing there, continuously glowing. That indicates that there is no information. So we are calling that. So sometimes that mistakenly all three lights are glowing. Then we are calling it as, and it is a noise. You are not going to do bother about it. Okay, so signal means a physical quantity that should carry some information. I am singing some song. I want to drag your attention. I am passing some signal. Then that's what I'm calling it as a signal. I want to drag your attention. That's what I am stimulating you by means of pinching or by means of sound, creating some sounds, or by means of touching you. I am passing the signal. Okay, so the sensor, the outcome of the sensor is, okay, creation of the signal, or then we are calling it as a data. So in our human body, we are having different sensing organs for taste, for sight, visual, or touching, smelling, and hearing it. Okay, so in the day-to-day life, without smartphone, nothing is there. Now we can live without anybody, any relationship. But without some smartphone or mobile phone, you can't survive yourself for an hour. Okay, it is very difficult. Without wallet you can go anywhere, but without this sorry, without purse you can go, but without your now we are calling that as a wallet. Okay, that is our life, no? It replaces camera, it replaces the wallet, it replaces everything now. Okay, so with the mobile and there you are not at all feeling the loneliness, but the mobile phone is not there, you are feeling loneliness. Even your father and mother and wife and kids are with you, but you are feeling loneliness without the mobile phone. So smartphone is a part and part of life now than that of your organs, your own organs, like your eyes, your ears, and your skin or anything. Better than that, you are loving your mobile phone nowadays. So mobile phone also now interacted with you through the sensors only. Okay, so similarly, just I am taking one or two sensors. A lot of sensors are there. Okay, so your eyes are now mapped with the camera, and ears are mapped with the speakers, and your touching is mapped with your screen, touch screen. Okay, and you are using all these one or two only. I have there is n number of sensors are there. One of the assignments I have given to my students to write the sensors in the camera. Okay, and its principle of operation, everything they have to submit it as an assignment. Okay, students searched in all the things, all the media, and they have written nice assignments actually. Okay, so if you want to study about the sensors, you can just analyze about the mobile phone, what you are carrying, what are the sensors are available. Okay, but you should know the difference. As a technological person, you should know the difference as well as the principle of operation of each and everything. So what is accelerometer, what is gyroscope, what is the difference between accelerometer and gyroscope, what is GPS, what is touch sensor, what is the principle of operation there, what is a magnetometer, and what are the light sensors are available within that. Okay, at least you should know something, some concept about it. Okay, so this gyroscope, just I am not going to go and take in depth, but I just in a glance I will tell you what is gyro. Gyro, just you are going to measure the angular velocity, that is the angular displacement. Okay, so it will indicate the angular displacement. Then what is accelerometer? What is it? Just gyro, just you can see it detects the current orientation of the device or changes in the orientation, the rotational spinning, turning velocity, that is angular. That's what it is, angular. Okay, so you can see a mass at the center. Okay, and it measures the angular rate is always with respect to a velocity of how quickly the object is turns. So it is used, highly used for the camera as well as your AR VR applications of your mobile, and the games we are much more used for this gyroscope. Okay, and accelerometer also the same principle, but that is going to measure the linear acceleration. Here it is an angular moment, and there the linear acceleration. Okay, so the principle is vibrating structure of the gyroscope. A vibrating mass is placed in the center of the chip. Okay, that's what this is what. Okay, whenever an electrical signal goes through it, the mass will be vibrated. Okay, so moving the phone will cause the changes of the electrical signal. So the vibration is proportional to the electrical signal. That's the thing we are calling it this as a sensor. Vibration is an occurrence. Okay, it is a quantity. It is going to convert it into a signal. You can call it as a transducer also. Okay, what is the difference? A slight difference only. Whenever the signal is generated, then we are calling it as a transducer. Okay, electrical signal is generated, we are calling it as a transducer. So we can call the gyro as a transducer also. So you can all the games like your moment of car games and other games we are using within that of the mobile phone, where that this gyro is incorporated. And accelerometer, just you are going to tilt your mobile phone, okay, in the vertical and horizontal mode. Then that is what it is called the acceleration. The acceleration, just it is going to measure the linear acceleration. So different ways we can make the accelerometer. The capacitive type is there, and piezoelectric is there. Here, that is, I am showing the piezoelectric. The piezoelectric means it is a crystal principle. When you are applying the force or the mass due to this, now you are calling it, this is the acceleration. The acceleration is now converted into the electrical voltage. Okay, whenever force is applied. Okay, for acceleration, what is the formula of the acceleration? F is equal to ma. Okay, a is equal to f by m. Okay, yeah, sorry, f is equal to ma, a is equal to, yeah. Okay, so you are applying the force on a mass. Okay, so that is nothing but that force is applied here, and because of that the acceleration happen. That is used to find why it is widely. This is just I am showing for this mobile phone, but this accelerometer is widely used in automobile applications also. In your automobile, sorry, in your automobile applications for this airbag, when this vibrations takes place, that is heavy vibration. That is normally in the acceleration is only sensed in that of your airbag applications, but this gyro and these things, as well as or all times they are interconnecting those things. Okay, that is all dimensional vibrations should be measured. This one is just it is going to take the linear accelerations, and rotational angular moment is taken by the gyro, and combine these two. This will be, these things are used for many applications in your ABS systems, in your airbag applications also. This gyro as well as your accelerometer is used. Okay, so this is the case. Just I am putting for only for mobile applications. Okay, that features of this one accelerometer and gyros, linear accelerations, and the reference point is the gravity. The reference point is the gravity. This is your angular moment or angular velocity or angular rate, and tilting is tilt your thing. Okay, just the horizontal moment or the vertical moment, that is you are tilting your mobile phone, is sensed by means of your accelerometer. It is not by the gyro. And the rotation is detected by the accelerometer as well as the gyroscope, but accelerometer is showing the poor thing, but gyroscope is giving you an accurate thing for this one. And drift, this is a property. Okay, dynamic property here, that is a low drift, but a gyro drift can accumulate over time. And noise, these three are the properties. Okay, that is the drift, noise, and power use. Okay, so low power, and the gyroscope automatically normally it is using the high powers, and this is the higher noise, and this one gyroscope for wherever you want low noise applications, you can use this gyroscope. Okay, so these are the comparison of the accelerometer and the gyroscope. The basic principle is the accelerometer find the linear acceleration, and gyroscope is for the angular velocity. And next is the light sensors. Okay, so now you can ask me why in this class you are teaching all these things. Okay, here this gyroscope and the accelerometer, you see the materials what they are using. Okay, here this this mass as well as this materials what they are going to use when you are replacing with that of your here also. Okay, you are you going to use your rare earth oxides as well as the thing, the property will change, that we will see in the last 2-3 slides. Okay, so this light sensors also, that is when automatically the brightness as well as and the contrast will increase or decrease in your mobile phone by means of this light sensors. So the sensor placement is in this position, Okay, the proximity sensors and the light sensors are that together. How this gyro and accelerometer is working together. Similarly, this light sensors and the proximity sensors are working together. Okay, so that's what now the here the proximity sensing normally they are using is the infrared proximity. Infrared sensors can be used for proximity. Proximity means always a position. Proximity that means always referring the position. So if you are placing your mobile phone closeness to your ears, automatically your touch sensors will switch off as well as your brightness will come down, okay, to save the battery. So that is by means of this proximity sensors as well as the light sensors are acting together. So here we are using the photodiode. That is the light sensors. Normally, whenever the light sensors, it's a simple light sensors, the photodiode. When this is called a smart structure. Initially, I told you know that a smart sensors normally it consists of one processor and this is the sensing element. This is just the normal sensor. Photodiode is a normal sensor. What happens when the light falls on this? That is photodiode always it to create the output signal. Okay, signal means here it is a voltage. Okay, so that is output signal is created. Also output signal is created, that signal should be amplified. That signal is not able to pass much distances, very small, very weaker signal, that should be amplified. And that should be in time, in some cases it should be filtered, and then it should be converted into digitized, and then it should be processed. Okay, so entire thing is called the your smartness. Okay, or if it is they are fabricating through the CMOS technologies, that is called our IC. These are all we are looking in terms of the ICs only. But these sensors are conventionally available. Okay, this photodiode is conventionally available. Single diode you can get it from any shop, that electronic shop, that photodiode. Okay, in the normal that light automatic lighting systems we are using say single photodiode only. This is simple photodiodes only, photodiode arrays only. Okay, so when the miniaturization starts required, we require that is integrating into that of the chips. Okay, so integrating in the chip, it is giving that the smartness is injected there, or intelligence may be injected there. Okay, so you now you understand the principle. When light, so light intensity, according to the light intensity output signal vary, the strength of the signal varies. Okay, concentrated light is coming, the output signal is high. Okay, so according to that the sensor will act. Okay, or the sensor will create some signals. The signals is used to control the entire device, control the entire device. Okay, so you can see that detect how close the screen or phone is your body or any object, and that is approximation. Okay, approximation, this is the light, don't confuse both actually. Okay, ambient light and the proximity. So proximity is the position. The proximity sensor we are using the IR. Okay, infrared radiations. So IR always you are using this photo transmitters and this one, and the signals from that of this proximity, when some obstacle is coming, for example. Okay, so somehow this object is coming to close to that, automatically this the signal variations will takes place. So the variation of the signal is proportional to that of your position. Okay, so here you can see that the target object is there. Target is your body. Now the emitter and receiver. Okay, so optical signal pulses is pulses are coming, like your light sources, or that is your LED here. Okay, so that is our IR transmitter, ion port, IR receivers are there. According to that, the position is sensed. So up to this, these are the basic things we are using in our smartphones. Okay, so next is the magnetometer. Magnetometer normally in our smartphone, that is a compasses are there to find the directions and other thing. There are two type of sensor we are using. That is, one is a magnetometric dimension. That is, it shows the direction east, west, north, south. Another one is your direction through the GPS, through your, it is incorporated with your map. Okay, so magnetometer, this magnetometers are heavily used with respect to your strength and direction of the magnetic field. Okay, so using this principle, next slides, following slides will show you how this magnetometers or this magnetic effect can use as an inductive sensors. Okay, so before that, I will tell you one of the thing how this all this sensing will takes place. You have seen all these things. Okay, so some due to this, there is the external parameter. For example, here what happened when the light is falling on the diode, due to that the external voltage, the conduction through this diode is going to vary, or that this diode is now creating, or that is the voltage passing through this diode is going to be vary according to that light falling. Okay, similarly here the previous cases, what happens when the force is applied, according to that, when the high force is there, more, this is a property, piezoelectric property means when we are applying the force, EMF is generated. Okay, so these are the principles. Without this principle, we can't study about the any of the sensors. Similarly, in the case of the gyro and accelerometer, so basic principle is very important. So here is here this magnetometer also, what happens, this strength and direction of the magnetic field should be measured. Okay, so absence of the strong local fields, this will measure the ambient magnetic field of the earth. So ambient magnetic field means what? It is the north pole and south pole, the magnetic field in between across those things, we are calling it as this one ambient magnetic field. Okay, so this one determines the angle by which the device is rotated related to the earth's magnetic. So here this earth magnetic field is a reference. Here we are a similar thing. Here the gravitational force is the reference. Here the earth magnetic force is the reference. In the accelerometer, the gravitational force is the reference. Sorry. The gravitational force is the your reference here. That's what this accelerometer is also used for, the sun falling sensor. Okay, when somebody is trying to fall, means that fall deductions and all the things, we can use this accelerometer. Similar, since that's one person is falling, means that is against this gravitational force, he is falling down. Okay, similarly here this the magnetic field, this is the reference point. The gravitational magnetic field, sorry, this Earth's magnetic field is a reference point in the magnetometer. Okay, so this magnetometer applications are in the compass, detects the magnets, force or force field, and magnetic shield strengths. Okay, so similarly, next sensor is the GPS. Okay, what is the full form of GPS?
Global positioning system.
Very basic actually. Okay, so what it does actually, how this GPS, what is the principle of GPS?
Triangulation.
Yeah, triangulation is the terminology what I am using. Okay, but it is instead of, it is not triangulation, it is trilateration. Okay, so trilateration means the four satellites are, that is in that is the distance between, that is the formula is distance equal to signal travel time into the speed of the light. Okay, so the signal that is the satellite communications. In between the satellite communication, three satellites gives the indents, how it is going, that is xy is at axis of this sphere, and the fourth one is fourth satellite is now the correcting the clock factor, that is the time. Anything? Hello? Hello?
No, sir.
Anybody try to tell anything? Hello?
So please,
So I can't see the screen. That's what I'm asking.
So please continue.
Shall I continue?
Yes, sir. Yes.
Okay. Anything you want to communicate?
No, sir. No.
Okay. So all these fundamentals, okay. So that triangulation of the cell towers and Wi-Fi network, these they are using, but the principle of the GPS is trilateration, not the triangulation. Okay, and it is mainly used to in the mobile phone. It is used for the cell phone tower and Wi-Fi network. In your map, it is incorporated there in your map, and your the positioning everywhere, everything that is by means of this GPS sensors. Okay, so how it will detect the location? So application starts that listen for the GPS network updates, catch network location is retrieved, and GPS location is, so that how these locations are interlinked, and how it is going to be estimated best. That is the fourth one is doing. Okay, fourth one is it is correcting that and that the errors, and such a way that a GPS sensor is uh, used in your thing. And space segment, it is a GPS satellite, and control segment is a tracking station. User segment is the GPS receiver, and precise positioning service is by the authorized user, and standard positioning service is your civil users worldwide use of the SPS, and GPS satellite signals are SPS transmit to microwave carrier signals, that is L1 and L2. All these things I am taking means it goes to the communication side. That's what I want to confine it within the sensor only. Okay, so it is used from the 1973 onwards in the Department of Defense, and designed to assist the soldiers and military vehicles, planes, and ships in accurate determining of the locations. And 24 satellites for the six positions. Okay, six posts it is used, and okay, that's enough. Uh, Next is other sensors. What are other sensors we can use in our daily life, day-to-day life? Where temperature, some of the sensors, these are all up to this mobile phone. Now you can also explore much more in this, and just I have taken the limited one only. Okay, what are all other sensors used? Please go ahead, and you should know, since we are day-to-day we are using and our mobiles. Okay, so then the temperature, proximetry, accelerometer, some of the things repeated, and IR sensors. IR sensors can be used for your positioning, that is a proximetry, as well as the detection also. And pressure sensors, light sensors, ultrasonic, smoke, gas, alcohol sensors, touch sensor, color sensors, humidity sensor, tilt sensor, flow and level sensor. I hope many of you are doing your PhD, or many of you have already done your PhD. You can just take a literature survey on your sensors in the home automation system, sensors in the robotics, sensors in the your mobile phone. What are the basic sensors used, or what are the advanced sensors used? How, what is the gap in the day-to-day life, and what is a pain point? And if you are able to address all these things, you can generate one best good review paper. Okay, so please try in that aspect regarding the sensors. Similarly, those who are well versed in the robotics or any other area, you can find what are the actuators are used, as well as this IoT system, what are the actuators are there, and the sensors, how much the sensor is important, that much the actuators are important. Control side means you should know about the control logic. Without that, you can't develop anything. Okay, so controller means that what are the control algorithms available, how to optimize it, what are the parameters, all the things that you should know. But with your basic knowledge, you can write two, three things with respect to your IoT sensors, IoT actuators used in IoTs, in the robotics also, sensors and actuators. Similarly, you can take your mobile for smartphone also, what are the sensors are there. These are the simple ways. You can ask your students to develop some papers based on this one. Okay, that is why you can explain the fabrication technology, what are the gaps there. Okay, so temperatures, similarly, what are the left out only I will cover in this area. Okay, what are already we have dealt, I'm not going to cover. This temperature sensor, what is the principle of operation? There are different temperature sensors there. Now we know LM35. LM35 is a CMOS technology, that is a semiconductor based sensors, that are not a semiconductor based, IC based sensor. Okay, so what are the other sensors are available? So how this temperature is sensed, that is a basic thing. So already I told you. Now you forget about your smartphone and other thing. Okay, smartphone thing up to GPS only I have covered. After that, now I am going to take the common sensors, other sensors. Temperature sensor we are using in many places, in our cooking systems, as well as in our air conditioning system. Everywhere this temperature sensors is used. Okay, what is the principle of operation? Okay, so already that principle of operation may vary based on the material what they are using. Material they are using. So either what are the materials? We can classify the material into three types. One is a conductor, another one is a semiconductor, another one is an insulator. Anyway, insulators cannot be used for the sensors. Only we can use the semiconductor and the conductor. Either conductor can be used or the semiconductor can be used. What is the difference between conductor and the semiconductor? Anyone? What is the difference between conductor and semiconductor? Which one is differing this in the conductor and semiconductor? The bondage of the atoms. Okay, so in the conductor, a large number of the free electrons are there. You know, the flow of electron is called the current passing through that some particular substance. So lot of free electrons are there in your conductor area, but in the semiconductor, what it is, there is no free electron, but it is tend to release the free electron. Either you are applying some force on it by means of beating it, or by means of heating it, or by means of applying some external potential, so the free electrons will be generated. So conditional based. Okay, so with this when we are heating, what happen in the conductor, what happen in the semiconductor? Okay, when we are heating, now I am not going to take about the atom position in the conductor, since a lot of free electrons are already there. One metal rod is there, just I am heating it. I just am heating a metal rod. So metal rod consists of a particular cross sectional area, particular length. By means of heating, what happens? Its cross sectional area is going to reduce. Okay, so its cross sectional area is going to reduce by means of heating. At one point, it will going to break down. Okay, I'm not going to make it to melt down or break down, but I am heating it. Because of that, its cross sectional area is going to reduce. So cross sectional area reduce, but length is going to increase. Okay, so the formula for this resistance is R is equal to rho into L by A. Rho into L by A. So rho into L by A, rho is the property of the material, resistivity of the material. If I am using the copper, means it has one resistivity. I am using aluminum, it has one resistivity. The length and area is now going to vary. Okay, so now in our case, length is increased, the area is going to decrease, the R is going to increase. So in the metal, when I am heating it, the resistance is going to increase. That is a conductor. When I am heating, the resistance is going to increase. Okay, so this principle is used for the temperature sensors. So temperature sensors, it is called the positive temperature coefficient. When we are heating, the resistance is going to increase, means positive temperature coefficient. That sensor is called the RTDs. But in the its counterpart, semiconductor device, when I am heating it, okay, when I am heating it, more number of the free electron is going to be generated. That's what the resistance is going to decrease there. That is called the negative temperature coefficient. So these principles are going to use to construct the sensors. Okay, you may ask me that you told the sensor is going to produce the signal, but here resistor is not signal. Resistance, the property change only happen. So how this property change is converted into signal? That's what I require some signal conditioning circuit. Okay, so this property change, resistance change, is converted into change in voltage by using some bridges like your Wheatstone bridge or your potential divider circuit. You can convert this change in resistance into change in voltage. Once you get the change in voltage, that is going to be amplified, then converted, and you can transmit to anywhere you want. Okay, so this is the basic principle how this temperature sensor is used. Then you may ask, there is no way of converting the temperature into voltage directly by means of a sensor. Yes, it's possible. It's possible through the thermocouple. So the thermocouple, what happened? Two dissimilar metals join together. One junction is going to act as a cold junction, another junction is act as a hot junctions. Okay, then EMF is generated. So when the hot junction means where you are going to heat it, the temperature variation takes place. Another one you are making it the constant temperature junction. So automatically the EMF is going to generate the output. So thermocouple gives the thermoelectric effect, and the RTD and the thermistor gives the thermoresistive effect. So any one of the effect we can use or fabricate, and we can show it as an fabricated sensors. Okay, so this is the basic fundamental of the temperature sensors. Now here, how we can use this rare earth elements by means of this rare earth elements, just we can see that their properties of the magnetic property and photo resistive property, and their catalytic properties. These three properties we are going to utilize in our sensor technologies. Okay, there the one no, lot of properties are there in the rare earth materials. I'm not telling about the rare earth oxides, rare earth materials. Okay, but I'm going to utilize these three properties only today. That is a magnetic property, as well as this photo property, photoresistive and photoinductive property, as well as that catalytic properties. Okay, so any one of these properties, how it is going to be used for the sensor fabrication, that we will see it later. Okay, so these are all available. I told that thermistors and this IC sensors, this is RTD, and thermocouple is there. You may use it in your laboratories. Okay, similarly this humidity sensors. Okay, humidity, the amount of water vapor in air is called the humidity. Okay, so humidity variations is sensed by means of your humidity sensors. It is an humidity also, that is the temperature here also, the relative temperature and the ambient temperature is there. Relative temperature is by means of your thermocouple. Similarly, the humidity also, your relative humidity is also there, and you are, and frost point is the variations are in the parts per millions, variations may occurs in the, that is particles, no, that is moisture particles, how it going to vary there. Okay, so whenever this humidity variations takes place, any one of the parameters, as I said, the resistive parameter is varying, or according to that, the output voltage variations takes place. That is the principle of your humidity sensors. Okay, there also nowadays this MEMS sensors are available. That is a fabricated thing. Similarly, this motion sensors. Okay, so motion sensors, this infrared can also be used as your motion sensors. Infrared can act as in two things. One is this proximetry and passivity test. Okay, passive infrared and the proximetric infrared. So one will find the proximetry, that is a position here, that is finding the motion, that is in all our toys, maximum our toys we are using this IR sensors as our the motion sensors, like kids toys. We can see that transmitters, IRs are transceivers are there, transmitters and receivers are there, and according to that the moment can be sensed. Okay, you can find similarly your ultrasonic sensors also can be used. Okay, and different types like magnetic motion sensors are also there. Magnetic, there's a magnetic effect is very much used for the motion sensors. That is fundamental of your Faraday's law. When a conductor is moving in a magnetic field, EMF is generated. Okay, so that conductor is moving means that a conductor moment or the motion can be sensed by means of the variation of the EMF. Okay, similarly, the distance between that your object and your IR thing will find that how long, how away it is moving there. Okay, so that is your motion sensing will be used. That is, this is a non-contact type and the contact type sensors. But in your magnetic sensors, maximum there there is also contact as well as non-contact type is there. But IR is a non-contact type sensors we can apply there. Okay, so this is IR motion sensors, and similarly this chemical or smoke, that is electrochemical that principle we are using or detecting that we know how that alcoholic sensors are used there and how it is sensed by means of this that is the chemical or the toxic or some other the smells and other in your gas leakage and all the places we are using this smoke and gas sensors. Okay, MQ6 is used. I know all the things. And similarly, the pressure sensors, we can use our piezoelectric effect or strain gauges or load cells can act as your our pressures to find the pressure as well as the load cells. Basic thing is your strain gauge can find the force. And what is the difference between the force and the pressure? Okay, so that is a direct and indirect measurements. Similarly, Bourdon gauge is there, bellows are there. How they can be interconnected? Those things just you can apply your analytical formula. Okay, pressure equal to force per unit area. Okay, P is equal to F by A, force per unit area. And what is the difference between this pressure and the stress actually? Okay, the pressure means the force applied, both are the formulas are equal. Okay, same only. But when the force is applied on the confined area, then we are calling it as an pressure. But in the force is applied on the open area, we are calling it as an stress. Okay. So we know that this tire in our automobiles nowadays, if you are using your car, by n number of sensors we are using. Okay, your speed sensors and pressure monitoring, tire pressure monitoring sensors. These are all the non-contact type only we are using in many places. And accelerometer we are using in this your airbag systems and this accelerometer. Many type of the accelerometers are available. What I've already shown in your thing is piezoelectric type. Similarly, Hall effect accelerometer. You know what is a Hall effect? Okay. Hall effect, I will show you when that's a magnetic field is affecting the output voltage. Then that effect is the Hall effect. That is by means of the Lenz law. And that is eddy current is the Lenz law. This is Hall's effect actually. And a capacitive type of the accelerometer is there, and a piezoelectric accelerometer is there. Okay, so capacitive, how this capacitive effect also can be used. Earlier I explained you about the resistive effect. Similarly, capacity effect. What is the formula for the capacitance? I cannot cover all the things here due to the time constraint, but I will give you some insights that, okay, the capacitor consists of two plates and one dielectric. Okay, so that the formula of the capacitor, just you can see that. Similarly, how R is equal to rho into L by A, your C is equal to epsilon naught epsilon R into that what it is, area and the distance. Okay, so it is affected by means of the distance between two plate, overlapping area, that dielectric constant. These three are the variables here. Okay, these three are the variables. So when this distance between the two plates are varying, or the dielectric medium is varying, or the overlapping area between these two plates are varying, according to that your output is going to vary. Okay, so capacitive sensors are more accurate than that of the resistive type of the sensors. Okay, so this capacitive type can used as an that level measurements, water level measurement. So just we are varying the distance between these two plates by means of the level. Automatically, the output voltage is going to vary. So capacitance, similar thing. Variation of the capacitance is converted into the variation of the voltage by means of the capacitive bridges. Whatever you have studied in your basic level, that will be very much useful for your research as well as all the things. Okay, so the how this variations of the capacitance. Similarly, the inductance parameter variations. Okay, so whenever the variations of in the inductance variations takes place by means of the self inductance as well as the mutual inductance. Those things we will. I cannot cover those things. Anyway, these three variations just to keep in mind: resistance variation, capacitance variations, and the inductance variations. Okay, so basic resistive type transducer or sensor in your day-to-day life you might have seen is, or in your laboratory you might have seen is your uh, potentiometers. Okay, when the potentiometers, that can be used for distance measurement also. Okay, there's already we have seen it. And this is another one, the ultrasonic effects for robotic applications. It is mainly used for finding the obstacles on its path. Okay, and the navigations applications also, this ultrasonic sensors are used by means of this ultrasonic effect. Okay, then LDR already we have applied there in our light sensors. Okay, that according to this, here it is, that is a photodiode. This is a LDR. LDR means what? Light dependent resistor. Okay, so whenever this light intensity varies, according to that, the resistance of the that material varies. That is your the principle of the LDR. Okay, that we might have used in all the projects in our small projects. We have used this LDRs. And the sound sensors also, your normal sound sensor, your microphone, and the other devices, you can use this. And diaphragms can also used in the microphone. Within the microphone, we are using this diaphragms as a sensor, internal sensors. Similarly, that touchings, or we are calling it as a tactile sensors. There also the same thing. In your early stages of your mobile phone usage, you can easily understood that the capacitive touch, how it takes place. Nowadays, it is a by means of that sophisticated sensors are there, but this capacitive and this resistive type sensors, when that is contact type only, that all the touch sensors are mainly with respect to the contact type. Okay, when we are touching it, the contact is closed or contact is going to open there. And the colors also, that is a variation of your reference color RGB. Okay, so when it is passing through this object, that is this which one is going to be reflected. Okay, which color is going to be reflected, that is a particular color of the object. And the combination of this RGB also gives you the different colors, like your other colors also, yellow, green, and blue. All these fundamentals you might know. Okay, so these are all the color sensing nowadays, but the fundamentals are very important. You can purchase a color sensor and fix it in your project, but the fundamentals is very much required, and that if you want to generate the signal conditioning circuit and other cases. And what is this is very much important with our rare earth materials. This is the magnetic sensors. The magnetic sensors utilizing the magnetic property of the materials. Okay, the magnetic property of the material, that magnetic sensors are used. We know the magnetic may be, that is electromagnet or the permanent magnet, and temporary magnetism also available there. So how these things are takes place, you will see that in all the other things, the temperature, pressure, strain gauges, and photos, diode or light sensors, it is directly giving you the output voltage. Okay, but here the variation of the magnetic field should be created by means of all these things. All these things, any one of the parameter is creating the variation of the magnetic field, then that is going to affect the sensor property. Okay, so then out the output is coming, that is the between the difference between the normal sensor and the magnetic sensor. So here the magnetic field is going to be affected by means of something, then we are calling it as a magnetic sensor. Okay, okay, you see that when this rotating, like this is all of you know, this is a tachometer, how the principle of operation, because of this rotation, this magnetic field is going to vary, or this we are calling the flux lines are going to cut. According to that, the EMF variations is takes place. This is a basic fundamental law. Okay, the fundamental law is used to develop the sensors. Okay, and the ferromagnetic wheel having tooth rotates, it changes the flux in the coil and result in the voltage reduced. Okay, and the frequency of this voltage depend upon the speed of the wheel. This is used for the speed sensors, okay, or tachometers. So differently, similarly, we can find about the position by means of this magnetic sensing, and speed, as well as the rotating, that it is mainly used for this motor applications as well as the robotic applications. This magnetic sensors are mainly used for this proximity also, and it is used for speed sensing, and it is used for this motor controllers, And similarly, this inductive also, there are two things. One is a self induction, another one is a mutual inductions. You see, this is one of the important sensors, like it is called the LVDT, linear variable transducers. Okay, and differential transducers. It has one primary and the secondary winding and a core. When this core is, we are applying the displacement on this core. So the displacement, which device you want to find its displacement, you are connecting here. Okay, this is a contact type. There is no non-contact type the effect here. Just we are connecting here. The core is moving inside and the outside. You see, these two are the secondary windings, and this is a primary winding. When the secondary winding is overlapped, okay, the complete overlapping is takes place, the output EMF is equal to 0. Okay, and the displacement is takes place the inner side. Then this secondary is going to, this secondary 2 is going to overlap with the primary. Okay, and when it is the outer side, the secondary 1 is going to overlap with this. So output voltage, the equation is very important. The output voltage is equal to the difference between these two voltages, ES1 minus ES2. Okay, so according to that, you will get the voltage in both direction, positive direction as well as the negative direction, positive voltage as well as the negative voltages. Okay, so this is a simple coil mechanism, you see. Okay, whenever here we are applying the displacement, you know that the difference by the transformer principle, one primary and the secondary, and the core is there. The same thing is used here, that is a transformer. Similarly here, it is the inductance principle. When we are passing this voltage or this one, the current that this coil is going to be get energized, and because of that this magnetic force is created. And when we are making this displacement, according to that, this attraction or the repulsion will be takes place. So this is the principle here. Single winding of the central limb of the E-shaped paramagnetic body is excited with an alternate voltage. Okay, so now this displacement to be measured in, applied to the I is equal to V by omega L for this fixed value. So every sensors you can write this equation, this type of equations. Okay, once you are able to write this equation, then we can find or relate the parameters. What are the variables and which one we want to find it, and which is the unknown. So unknown parameters we can find by from the known parameters of the sensors. Okay, so next is similarly this eddy current. The eddy current also the principle of the Lenz law. It is a non-contact type sensors. Okay, when you see that the magnetic field is there, when we are this probe is coming very close to that, this is very much used for this approximation. Okay, so when this probe is coming close to this, according to that, the pattern magnetic field is going to vary. The variation of the magnetic field is proportional to the closeness between these two. So this is called the eddy current. And next is a Hall effect. Okay, so all the histories are not required. Now you see that this magnetic field. Okay, so due to this magnetic field, the EMF is going to vary. This is the effect. This effect is called the Hall effect. Okay, so just you can imagine that. Just a minute. Okay, so this output voltage variations is now amplified and taken out. Okay, so this Hall effect is also used for the position sensoring, as well as mainly used for this motor control applications and the position. And here this magnet field is very important. This just you can think of this magnet. This magnet is made up of what material? This concentration of the field is depending on this magnet. Okay, so this life of this the efficiency of this sensor is highly depend upon this magnet only. Okay, so what material we are going to use this magnet, that will decide our this efficiency of or the accuracy of this sensor. Okay, so how this sensors are going to be integrated into the system, that's what I have seen. I am going to show you that the sensors and are integrated with that of your controller, and this from the controller, all the parameters are that we are giving our desired things there, and different sensors are coming. So that's what now computer based controls are there. So all the inputs now, for example, computer based control means not only don't think of this computer only, like your microcontroller, your PLCs, your distributor control systems, everything is will comes under your computer based only. Okay, wherever the processor is using, we are calling it as a computer based controllers. So all the sense from the all sensor nodes, we are giving them to that of your processing unit. Now I am calling this computer as a processing unit, and the processing unit already we are the inbuilt algorithms are there. The algorithms, according to the algorithm, it will process the inputs from that of all the sensors. Okay, and then it will create the respective command, and that command is going to the actuator. The actuator will manipulate some elements. According to that, the control will takes place. That is the principle of your feedback controls, and or any of the automatic systems. Okay, so all these automatic systems, the sensors are very much important. So now that I'm going to wind up with our rare, how we are going to integrate this rare earth in that advanced materials and the rare earth materials there. Okay, so now all the these 4-5 days you heard about all these materials, what is called the rare earth, where it is placed, and how it is going to be and be characterized, and how it is going to use for EVs and batteries, everything, everywhere. Okay, similarly, I will tell you how we can integrate into that of the sensors. Okay, so these are why here we are calling it as a main thing. All nowadays, all the sensors are the MEMS sensors. Okay, or nano sensors are the micro sensors. Okay, so this micro and nano sensors, micro or nano technology, that is we are calling it that. That's what all the sensors are fabricated in an ICs. Okay, and for that we require some dopants. Dopant means some additives. Okay, so by adding those these rare earth materials, one or two rare earth materials with that, then that magnetic or optical and catalytic property, already I told this is going to vary. This magnetic, optical and the catalytic properties are going to be vary. Okay, so luminance property, many rare earth materials like terbium and eurobium, that will glow. That all the things that they might have taught you, based on their chemical background and other things, and the periodic table. But its property is the material like terbium and eurobium, it will glow by means of when we are applying some force also it will glow, or by its nature it is glowing. Okay, so that's what these things are can be used for used as a stimulus in case of our color sensors as well as our light sensors. Okay, and we have seen that I told you that this the magnet of the Hall effect sensor is the main thing which is going to decide the accuracy of that particular sensors. Okay, so we are creating this is the magnets with high strong magnetic properties like your neodymium and that is and dysprosium, and that will create the strongest permanent magnets. Okay, that we will see it one or two. Okay, and similarly the catalytic, and just I'm telling about the rare earths, its oxides like some of the when oxides are used for the coating materials in the nano technologies. Okay, they are also increasing the strength of the materials, strength of the magnetic property, strength of the luminance property, and this electrochemical properties. The catalysts are normally used for the electrochemical properties. Okay, so magnetic sensors we have seen that mechanism is we have seen like the because of this like you can now think of the last one. What we have seen is a Hall sensors. Okay, so one permanent magnet is there, and due to the permanent magnet, according to that, the strength of the magnetism, that is your output thing, voltage is going to be varies. Okay, so there just I'm telling about this magnetic only. Okay, now I'm going to take this neodymium ND, that is your NdFeB, that we have studied in our school level also, that is NdFeB, that neodymium ion and boron magnets are very strong enough. Okay, what's the difference between, and another one combination we can use is samarium cobalt and which magnet normally we are using? Ferrous magnet. Okay, what's the difference between These things actually, where you can use ferrous, cobalt, nickel, all the metals you can use. And what's the difference between those magnets and this magnet is, okay, this neodymium ion boron magnet gives you the strong magnetic field compared to that of, even better than that of this samarium cobalt. But what is the advantage of this samarium cobalt means it can withstand at high temperature, okay, than that of your neodymium ion boron magnet. Okay, so according to our use, we can use either neodymium ion boron or samarium cobalt magnets. Nowadays, for the heavy industrial applications like your windmill and other heavy applications, you can use your samarium cobalt, as well as for this sensor applications we are using neodymium ferrous boron magnets. Okay, so they can be used for ABS wheel speed sensors and crankshaft position sensors. In robotics, they are using the servo motor feedback applications. The position application, main thing is control. Okay, and in the smartphones also, they are using this optical image stabilizations for auto focusing the actuators. Okay, and why they are critical? Why this we are calling this rare earth materials elements are critical for this sensor application is that is. Whenever we are going for this fabrication technology, the miniaturization is very, very important. Okay, what are all the parts we are going to be miniaturized? That's what till now we are struggling to miniaturize our transformers as well as the inductors. Okay, so this because of this rare earth materials, this magnetic part are going to be getting miniaturized in the fabrication technology. And as well as this IoT applications also, this rare earth materials, what sensors like your magnetic sensors can be used as an limit switches and rotatory encoders, and your consumer IoTs. IoT, consumer IoT means whatever we are using in our day-to-day life, and industrial means that is based on your industry applications only. And similarly, your yeah, all the things repeated. I'm going to finish it. Yeah. Yes. So next is the luminance property. Okay. So a luminance property that its basic principle is the rare earth elements ions are doped into the doping means we are adding the impurity, adding additive. Just we are adding some the rare earth materials or rare earth luminance material. Automatically, the luminance property of your normal sensor is going to be enhanced. Okay, so like where gas molecules or the temperature changes that can be sensed easily by means of doping these materials there. Okay, so that they because of this light emitting property and long luminous lifetime, they are very much used than that of the normal doping conditions. So what are the materials they are using for this luminance is your terbium, eurobium, and EU and ER. Okay, as well as your deuterium can be used for this for the fiber optics applications. All the fiber optics cables, like wherever you want to get the high luminance rate, we can use all these sensors there, and our sensors coatings we are using. Okay. Similarly, your this one electrochemical, that is catalytic property. Okay, so these three properties are very much important. That is your takeaways here. That your magnetic, luminance, and electrochemical properties. We are that our catalytic property. We are using the different rare earth materials are incorporated within that of the sensors and sensor fabrications. And you can see that how when the oxides are going to be coated for the nano material, how the efficiency is going to increase. That also there just your I here just I for a glance I have given only two oxides here, cerium oxide and deuterium oxide. That cerium oxide is used to for highly reactive to the oxygen. Because of that, it can be used for the gas sensors. Okay, and deuterium oxide is used to for the leakage of the fuel and the other things. It also used for the humidity also. And so all the electrochemical sensors, as well as your pH, all of you know pH level vary with respect to the acidity and alkalinity of the material. For that, we can use these rare earth materials. Okay, frankly speaking, I am not working on this rare earth materials, but I have seen that how these rare earth materials can be incorporated with that of what sensors I am using here, that and how it can be enhanced by means of using this rare earth materials there. Okay, this can also be that incorporated in your research area such a way that you can see how this rare earth materials will enhance some particular property. Like your only three properties I have covered here, that is a magnetic property, as well as the luminance, as well as the catalytic property. Similarly, other properties may also influence by means of this rare earth materials. So rare earth materials nowadays they are using like in India, that the history of the rare earth material they have surplusly used, then they stopped. Again, now China, it has abundant of this rare earth material. They refuse to supply to us. That's what now we again it is opened here. That is for the rare earth materials extractions as well as the usage. And nowadays they are using mainly highly for the defense applications also. So this is one of the potential area, and I thank the organizers choosing that correct topic there. And it is a novel topic also, how we can use those rare earth materials in our sensor applications and other things in our battery application. I hope earlier they have covered about the batteries, how they can enhance the battery using this rare earth rare earth additives, how it is. All the things might be covered. Okay, so do it for your research and enhance your research by means of adding all these things, whatever you have studied till now. So that's all from my end. Any queries, please ask. And don't ask me very core to that of the rare earth elements, but when the sensor part and the control part, I will answer to you whatever extent you want to clear from my end.
Thank you, sir. Dear participants, now it's your turn to ask questions or raise your queries related to this session. You can now unmute your mic or may post your questions on the chat box. And kindly note that the feedback for this current session is available in the chat box. So we have some questions already in chat box.
Yes, ma'am.
First one is, how does an IoT system work from data collection to user interaction?
Yes, ma'am. Yeah, one more time, please repeat it.
Okay, sir. How does an IoT system work from data collection to user interaction?
So IoT, there is a different platforms are used actually. The data collection is by means of the sensors. Okay, different type of the sensors we are using, like our and once you collect the data, that data should be stored in the clouds, and it should be processed by, and whenever like that different platforms are available. That what platform you people are going to work there, and based on that platform we have to that program there, and according to that device to device communications and the networking will take place, and uh, our data, the collected data will be processed there. Okay, data processing is very important aspect of this our IoT applications. Wherever you are going to apply, in what applications you are going to select for that particular case.
So we have one more question. What are the key limitations of current optical sensor technologies in real-world environments?
the limitations of real world environment is the main thing is with respect to your sensors properties. Okay, the optical sensors are mainly with respect to that is it has the efficiency and all the other properties like your accuracy and the precision and all the other things will be affecting that what are all other factors which are which are which are going to affect your hello, is it audible?
Yes, sir.
Yes, some network issues. Okay, so main thing with respect to your optical sensors is with respect to your all the interferences should be eliminated from there. Okay, so what are all the interferences in the optical communications or takes place? That is mainly with respect to the channel and their transmissions and receiving part. And what are the conditioning circuits whatever we are using there, and that will be with the main concerns what you have to taken place to consider for that.
Okay, sir. Thank you. Behalf of the organizing committee and all the participants of the FDP, I extend my sincere gratitude to our distinguished resource person, Dr. Glance Devdas. So your talk that enriched our understanding about this session and for delivering an exceptionally information and insightful talk on rare earth materials, not next generation rare earth materials in sensors and IoT applications. It provided immense value to all participants. Once again, thank you, sir, for your esteemed presence, valuable time, and for sharing your vast knowledge with us. Thank you, sir.
You're welcome, and thank you for the opportunity given. And anything you want to collaborate within the field of the control process control applications or this one, you can contact me, and you can get my contact from there. This organizers, and just you can I will share the material with them, and you can get my contact as well as if you just you can start from that of your basic things about the sensor applications, and you can classify some robotics as well as IoT applications and other things. Just you can try to develop some review purpose that will be useful for your what it is on our research journey. Wish you all the best, all of you. Thank you all. Thank you for the opportunity given.
Okay, sir. Thank you. Dear participant, it's time to our next session. For this session, it's my privilege to introduce and great honor Dr. Anandakumar S., an eminent scientist whose contribution to materials, science, and advanced ceramics have significantly enriched both national and international research communities. Dr. Anandakumar S. is currently serving as Chief Scientist and Head in the Material Science and Technology Division at the CSIR National Institute for Interdisciplinary Science and Technology, TVM. With a distinguished career at CSIR that began in 1992, he has risen through the ranks with unwavering dedication and profound scientific insight. He holds a PhD from the University of Chennai, where his research supported by the prestigious CSIR Dad Sandwich Fellowship. His academic journey also includes advanced work at leading international institutions, including in the USA, Germany, France, Italy, etc., reflecting his global engagement in cutting-edge materials research beyond research. Beyond research, his work exemplifies a commitment not only to scientific excellence, but also to mentoring the next generation of researchers. Please join me in welcoming Dr. Anandakumar S., a dedicated scientist and inspiring leader. Welcome, sir. Welcome to the session.
Yes, good evening, all of you. Thank you very much for the kind introduction. I am Dr. Anantakumar from CSIR NIST Trivandrum. Please give me a few minutes to load my presentation. You can unlog in your presentation. Yeah, good. Thank you. Hope you are seeing my slides.
Yes, sir, your screen is sharing now. Yes, sir, it is visible.
Is it sharing? Do you see my slides?
Yes, sir.
Okay, I'll go to the slideshow mode. It's okay now. It's in full scale.
No, sir. You
Okay.
can do slideshow.
Yeah, it's in slideshow mode. And thank you very much. And this is, oh, sorry. Uh, do you see my slides?
Yes, sir.
Yeah, but I am not seeing here. Yeah, okay. Okay. So what I am going to talk today is that I don't know who are all the participants. Basically, I am expecting the participants probably from chemistry background, engineering background, physics background, and I hope that the way we are working in CSIR NIST Trivandrum is jointly with IREL, Indian Rare Earths Limited, Kollam, and we are also closely working with JNARDDC, Jawaharlal Nehru Center, in Nagpur. And especially we have many projects from Ministry of Mines and Ministry of Steel and Ministry of Environment. Today, can you hear me?
Yes, sir.
Hello?
You are audible. Yes.
Yeah. So if any difficulty is there, please interact with me. And if I am not properly audible, please tell me. And for another 40 to 45 minutes, we will talk about rare earth material. And here in CSIR NIST Trivandrum, we are working very closely on rare earth materials. Basically, we are very fortunate to have our beach, especially from Kanyakumari to Orissa. The beach minerals, beach sand has lots of minerals. Basically, we have ilmenite mineral, we have monazite mineral, and we are very closely working with IREL. And IREL is the only authentic institute or agency to talk about rare earths, to sell rare earths, and to do marketing on rare earths. And today, rare earth is becoming a big, how can I say, it is industrially extremely important because just a month back, I was in Tamil Nadu government organized Confederation of Industry program exclusively on rare earth. Okay. And this rare earth is so critical today. And basically, the entire country, the post COVID, is closely changing to the innovative transport systems, innovative energy generation systems, innovative biomedical systems, and especially to do the cancer diagnosis, to also to do the how can I say, actually, the especially from the biomedical to space technology and to mobile technology and also to the transport sector, critical minerals is playing a very important role. And all of you probably may be knowing that today entire country is trying to tap the potential of critical materials, whether it is a rare earth or it is a gold or silver or platinum or palladium or graphene or molybdenum or gadolinium or gallium or scandium, all industry, everywhere, country is looking for the expertise and technology for making a scandium extraction, to make a technology for gadolinium and gallium extraction, and to recycle the silicon solar cell, to regenerate the silicon solar cell. Government is seriously looking, and unfortunately all these areas are high temperature processes. You must understand it. The silicon wafer technology, today India has no technology, but government of India has invested 77,000 crore rupees for silicon wafer technology, and scientists particularly in BARC, IAC Bangalore, IITs, they have enough human resource, and but unfortunately none of the institutes could bring down the silicon wafer technology. Still, we, our solar cell program, government of India is largely talking about solar cell, when the sun energy generation technology through photovoltaic solar cell, and people are working on dye sensitized solar cell. People are also working on perovskite based solar cell. People are working on thermoelectric based energy generation. But unfortunately, people like you, the faculties, you are only focusing on publications and short term benefits, and none of them are focusing their mind towards the long term benefit. And that is the reason that India is still not having an adequate technology for silicon wafer manufacturing, silicon wafer machining, silicon wafer etching, and even silicon ingot processing. Okay, and we don't have 99.999% pure silica sand also. And one thing I would like to tell you, that engineers like you, government is looking for the conversion of oxide to metal. Please note down this. Any one of you is interested in converting the silicon dioxide into silicon metal, whether it is for an alloy processing or for polycrystalline silicon solar cell processing, does not matter. But you people, the young engineers, you who are the the future of this country, whether they are electrical engineer or metallurgical engineer or mechanical engineer, the country is looking at new technologies, especially rare earth oxide to rare earth metal, and rare earth oxide to rare earth phosphorus, rare earth phosphorus to medical devices, and medical devices to diagnostics, and diagnostics to health care, and health care to rural health mapping. Today, government is pumping money on tuberculosis, that means TB program, but none of us have devised any mechanism to easily understand the mobile enabled technologies for monitoring the TB, monitoring the lungs. Okay, and these are all some of the small issues. Even after 77, 78 years of independence, government is still struggling where to get this kind of indigenous functional materials. So in that series, one of the other important area is a climate change. You also know, I also know that climate change is a serious issue, and air conditioning equipment, installation of air conditioning equipment in large scale buildings, either the shopping mall or the multi-floor government building, corporation office, hospitals, everywhere people are looking for green technology and clean technology, and more importantly energy saving technology. So this talk from CSIR NIST Trivandrum, for the last 20 years, we are working in the field of IR reflective pigments. IR reflective pigments, you all know that titanium dioxide, and titanium dioxide is derived from ilmenite, and more 4 or 5 companies are there in India, especially Orissa, Tamil Nadu and Kerala. Lot of people are investing on titanium dioxide processing from ilmenite mineral, but very importantly, ilmenite mineral which is freely available in the beach sand. Beach sand has especially Manawalakurchi, Kollam, Alapula, and also some part of Orissa. We have ilmenite sand. The ilmenite sand is nothing but Karimanal. Probably some Malayalis are there in the audience. They may be knowing about Karimanal. And the Karimanal is nothing but ferrotitanium. It's actually ferrotitanate, which is Fe2TiO3. From that, people are taking TiO3, and unfortunately, since it is derived from natural resources, people are not bothered much. And simply they take the ilmenite mud and they roast it with either coal or graphite, and the roasted ilmenite will be dissolved in acid, and that acid consumption high. And if you are an electrochemical engineer or a micro or a physics expert or mechanical engineer or metallurgist or chemical engineers, you can think of how to make this environment friendly, eco friendly ilmenite processing. That means ilmenite to synthetic rutile. Synthetic rutile. As far as my research is concerned, this synthetic rutile is very important. Since CSIR NIST Trivandrum is very close to TTPL, Trivandrum Titanium Products Limited, where titanium dioxide is manufactured out of sulfate root. For example, the ilmenite mud after roasting, it will be dissolved in sulfuric acid, and the economics says that to make 1 ton of titanium dioxide, the industries process 2 tons of ilmenite. And now you can see that if I take 2 tons of ilmenite, 1 ton of ilmenite is going to be the waste. Okay, it is a solid industrial waste which is developed by Triangle Titanium Products Limited, TTPL. So in NIST Trivandrum, we understood how this ilmenite mud, that means unreacted ilmenite, the 1 ton waste of ilmenite, how can we use? This is a question. This is a question that we have asked because it is a waste of the natural resources. Take 1 ton of titanium dioxide, selling that in the market, but wasting 1 ton of ilmenite mud for taking 1 ton of titanium dioxide. You produce 1 ton of waste. That waste has sufficient critical materials, especially rare earths. It has europium, it has scandium, it has gallium, it is also having vanadium, apart from zirconium, thorium, and uranium. So, as a scientist, it is our duty to find the most economical method to extract these high value products. So in CSIR NIST Trivandrum, we are working on extraction of scandium, extraction of gallium, and value addition and extraction of vanadium, and also we are also working on battery waste to extract gold, silver, nickel, cobalt. And across the country, everybody is investing it on lithium also. Okay, but fortunately now lithium ferrophosphate is replaced by sodium ferrophosphate, and sodium ferrophosphate is another energy battery material, capacitor material, which is already adopted by many automobile industries. Today we all have Mahindra car and Hyundai car and MG car. everybody introduced their battery models, and these batteries really in a, if you are a good energy scientist or energy physicist, you can easily convince any of the industries like Mahindra Hinode or Ashok Leyland or Hyundai Sandro. All those things you can convince them, and you can discuss with them for a magnet or a battery material development. So, what I am going to present today is that in line of this critical materials, in line of this magnet, in line of this rare earth, we are working in the area of energy saving, because as I mentioned that the air conditioning equipment installation is increasing day by day, and the company like Blue Star or the company like Carrier, they are all already fixed the target of 5 lakh air conditioners sales in the country. So why it is very dangerous to the country? Each and every air conditioning equipment is installed for the cooling of probably 12 feet by 12 feet room. Okay, 1.5 ton air conditioner is installed for cooling the 12 feet by 12 feet room. And if you go to cinema hall, if you go to shopping mall, everywhere the electricity requirement is keep on rising. Okay, and as far as the number of electrical air conditioning equipment installation is increasing, it produces enormous carbon dioxide. So government of India is also committed to cut down the carbon dioxide. Okay. So what I am working is that I am developing cool pigment. This is the new word for most of you. I am developing a cool pigment in such a way that this pigment reflect the solar energy in the wavelength of 500 to 700 nanometer. So this is what I am working for the last 20 years, and more than 5 PhDs have been produced in this area, and more than 3 technology transfers have been already made. And my purpose, my research is focusing more on India has plenty of inorganic colorants, whether it is red oxide or yellow oxide or green oxide or brown oxide or gray oxide, no problem. But none of these oxides, they have IR reflectance. So we are working on IR reflectance, IR reflective property of oxides. Why this is very important? If you come across Kerala and Tamil Nadu, they sell the terracotta tiles. The terracotta tiles have 30% porosity. And morning time, probably up to 10 o'clock, the house will be very cool, because you know very well that in Tamil Nadu and all, in Chennai and all, we normally lay the fired terracotta tile on the terrace only to minimize the heat buildup. But unfortunately, up to 10, 10, 15, this terrace board, that the tile, the terracotta tile body keep the coolness. Beyond that, slowly it accumulate the heat and up to 4 o'clock in the evening, it accumulates the heat, and after 4 o'clock, it releases the heat to the interior surface. And if you are all, any one of you are from Chennai, you can understand that to get the room cool, at least about 10:30 to 11 o'clock is required to bring down the room temperature. So entire country, or especially it is in Rajasthan or Ramagundam area of Andhra Pradesh or Chennai, because Chennai only 3 climates are there: hot, hotter, hottest. There is no cool. Only in the month of November and December we feel slightly cool. Otherwise, 10 months only hot climate only is there in Chennai. So people are looking for energy saving technologies, and one or two companies are there in Chennai who are selling the IR reflective cool tiles for the building application. And I am working very closely with Pidilite. I am working very closely with Ultramarine. I am working very closely with Whipfast. I am also closely working with Asian Paints. So all of them are looking for cost effective. The word cost effective is very important. Cost effective pigments. So let us discuss about this particular idea of IR reflective pigments out of rare earths. Okay, and this is the uh, see, not only building is looking for IR reflective pigment. Automobiles, I am working very closely with the Ferro Corporation, and also I am working with the Shepherd Color Company and Ferro Corporation. The purpose of Ferro Corporation is that because today we are seeing that everybody is moving towards battery technology, and the battery technology, if the battery power is used to cool the car, we may be losing the mileage. You agree with me? So, people are looking for the cool pigment technology, cool paint coatings technology for automobiles only to save the battery power. Okay. So, we are also working very closely on this aspect, how to reduce the heat penetration from outside to interior of the car, and we are working with the Tata Motors. Today we all are using 4G, 2G, 3G communication technology, and government has already rolled out 5G technology, and the car companies are very much worried about the microwave communication signal inside the car. Okay, they all are looking for dielectric coatings on the windshield, and also dielectric, ultra low dielectric coatings on the paint body. Okay, so please think about all those things. And so as I said that we are also working for a cool pigment for not only construction sectors like buildings, but also working with very closely working with Tata Motors and Mahindra and Mahindra company, and we are also now thinking about Ashok Leyland, how to maximize the energy utilization of a car, maximize the energy utilization of the passenger car from the battery technology. That is one aspect that we are working. And next slide is, for example, I told you that there is a material called lanthanum phosphate, and we are very closely working with lanthanum phosphate because IREL Kollam, they have lanthanum oxide and cerium oxide, and they also have praseodymium oxide and zirconium oxide, yttrium oxide, and we are taking only on lanthanum oxide and cerium oxide and converting that into lanthanum phosphate and validate the lanthanum phosphate for IR reflectance. And interestingly, we found that lanthanum phosphate has a similar IR reflectance to titanium dioxide. So, if the titanium dioxide is coated as a top coat and lanthanum phosphate is coated as a bond coat, we are able to save the temperature of at least 12 degrees Celsius in the roofing sheet. Okay, so if you reduce 1 to 2 degrees Celsius of indoor temperature in the building, you are going to save 15% of air conditioning energy. Okay, so that much advantage is there. And when we were doing lanthanum phosphate, slowly Government of India asked us to work on another kind of very interesting pigment, which is a red pigment. Today, if I am asking you, do you know what is a red pigment? All of you will say tomato red is a red pigment, iron oxide red is a red pigment. You will say those things. And similarly, whether the tomato red, organic red, or the iron oxide red, none of these colors they have IR reflectance. Whereas Government of India wants IR reflectance quality on the red pigment. And you know one thing, no? Whether it is a Maruti car or it is our Volkswagen, red color is very, very important, and red color is very attractive also. So everybody is looking for red color pigment. So government asked us to develop this red color pigment from cerium sulfide. So we worked on cerium sulfide IR reflective red color pigment from serous carbonate. And serous carbonate is one of the material already available in our IREL. And before going to cerium sulfide and from serous carbonate, we thought that why don't we develop the iron red color out of cerium oxide. So we doped praseodymium and iron oxide, and we found that this red color has thermal, I mean the IR reflectance of about 77%. If you have the iron oxide alone, it will not have that much IR reflectance. It will have maximum 27 to 30%. But in this case, we have 77% IR reflectance, and which is also showing a very nice thermal conductivity. I mean, very low thermal conductivity. You see, 0.0122, 0.02. So that much low thermal conductivity is there. So this is an ideal material for applying a coating on metal roofing sheet. And metal roofing sheet is a very popular business today. And industrial shed, even terrace buildings, everywhere people are applying this metal roofing sheets. So this is one of the pigment, and we have developed that pigment, and we developed a indigenous in-house IR lamp testing facility to understand what is the thermal heat built up of aluminum sheet, which is having only 2 millimeter thickness with and without coating, and we found that approximately 12 to 17 degrees Celsius cutoff is there when this pigment is coated on aluminum roofing sheet. And another very important thing is the black pigment. See, black body radiation everybody knows. For example, Scorpio car. Scorpio car, the most glamorous color is black. And if you go to if you go to Delhi, only posh people will use this black color Scorpio car. And the Scorpio car, you know, the engine capacity is very high, and the Scorpio car is also very attractive and highly priced. And so the color companies, the color making companies, they are asking, sir, how to enhance the IR reflectance of the black pigment. So in India, we have iron black or copper black. And these blacks and all is not having an IR reflectance as far as India is concerned. But the imported black color, which is having about 33 to 35% IR reflectance, and Indian companies are trying to imitate this foreign sold black pigment. So this project also came to us. We attended how to enhance the IR reflectance quality of the conventional black color. That was another next target. And we used our composite strategy. That composite strategy says that, as I mentioned you before, that lanthanum phosphate, blending of lanthanum phosphate with the conventional black color, we documented that the IR reflectance is increasing from 31% to 36%. As far as the dark color concerned, whether it is a dark brown or dark black concerned, even 1 degree Celsius improvement in the IR reflectance is a big matter. Okay, so here we have, but imported source is having 38% IR reflectance, and our indigenous source developed by CSIR NIST Trivandrum, which is having about 36% IR reflectance. So we are only 2% below. than the standard imported pigment material. So here also only rare earth has come to the picture, and these are all advanced materials. Whatever I am talking is all advanced materials, and it's all a new strategy for making a sustainable material. Okay, so you should not think that I am not talking anything irrelevant. These are all very much relevant to the advanced functional material and also advanced rare earth material. So another requirement also came from for making a green. You all know how to get a green pigment. The green pigment is possible only by chromium. And do you think that chromium will be permitted in Europe and USA? And but the MSME companies involved in pigment sector, they wanted an eco-friendly green pigment. So we have also developed the same thing in the lanthanum phosphate by introducing a multivalent dopants, and finally we have also got an excellent IR reflectance for this green pigment. So this was one thing you should understand, that any polymer, whether it is polyimide or PVDF or epoxy or polyester or polyurethane, yeah, all these polymers which are currently used for paint application, whether the polyacrylic emulsion or uh, polyurethane emulsion. Today, we all work for emulsion paints, and none of these polymers they have IR reflectance property. They have only less than 10% IR reflectance property, and this project also came to us. So we started introducing this IR reflective pigment modified by rare earth. We thought of putting it in epoxy, and we also found that the epoxy composites is having an excellent IR reflectivity because of these multifunctional colorants. And you all know that today roofing sheet means it's blue color sheet. Everywhere you can see blue color. And normally people are working on ultramarine blue. And ultramarine blue is nothing but copper, sodium, sulfate. And people are also, the industries are also looking for how to enhance the properties of this not only blue color but also the industry persons especially. Okay, so we have taken the blue color and we have done different experiments with different combination, and finally we found that the composite strategy is showing an excellent IR reflectance value, because this is for example, if you blend the rarer phosphate with ultramarine blue, the inherent quality of the IR reflectance value of ultramarine blue, which is roughly between 47 to 55%, that will go to 77 to 87%. This also we have demonstrated. And this is another nothing but this is actually you all know that cobalt aluminate blue is there, and we developed the bromite derived, that means ALOOH derived blue pigment, and we found that the so-called NIST blue pigment is having an excellent IR reflectance in the critical wavelength of 700 to 1100 nanometer. And coming to cerium sulfide, earlier I mentioned about cerium sulfide. It's a very tricky material, very difficult to make this cerium sulfide. Very impossible to produce this. Only one company in the world is producing this cerium sulfide red pigment, and we have also this project also given by IREL, and we started working on this particular this one, the cerium sulfide pigment. You can see here that it can follow the red color form only in this narrow window. Alpha, that means alpha cerium sulfide. Okay, very difficult. So we started addressing this issue, and we have made many experiments. Finally, with and without urea, with and without thiourea, and all we have checked. And finally, because the cerium serous carbonate is supplied by IREL, and sulfur is procured from the local market to make this cerium sulfide, and you can produce cerium sulfide, but you cannot produce a red color cerium sulfide, which is extremely difficult and which require a hydrogen purging, which also require a very careful monitoring of the gas pressure. Okay, and we have done it, and I'm telling you. And apart from that, other than the ceria-based red pigment, lanthanum phosphate-based green pigment, lanthanum phosphate modified blue pigment, we also have series of IR reflective pigments in our system. Mostly everything is rare earth based. And there was also an interesting inquiry for making a cool tile. How to make cool tile? I mentioned cool tile, the terracotta, but people, whoever is trying to minimize the concrete technology, that means concrete temperature, the heat build-up unit in a concrete, whomsoever is interested to decrease the temperature accumulation in the concrete, they all wanted a cool glaze. Okay, the cool glaze is also very important. We developed this technology and we have demonstrated this technology to academic institutes. And next is actually this is all nothing but the same IR reflective glaze was applied on a terracotta body. Earlier it was a porcelain body, and this is a terracotta body, and we have documented how much energy saving we can make out of this cool pigment technology. And this is nothing but an IR camera image to show that the surface temperature. And apart from that, we also worked on granules. Granules means silica, lantana, aluminum oxide granules, where it is nothing but a refractory granule, and this refractory granule is extremely important for holding your luggage. Okay, and this lanthanum phosphate and silica granule, whatever we have made, we have tested it, the thermal conductivity, and also we have embedded this lanthanum phosphate silica in the epoxy matrix, and finally we could make a super thermal insulation composite material. And very recently, the so-called what do you call that? Some of the industries who are looking for replacement of the refractory blocks with aerogels. Okay, aerogels is also another advanced material, and we are working in the area of aerogel for last 20 years. And here we try to make the aerogel blanket for the as a heat exchanger liner. Okay, today everybody is using a very expensive, very heavy refractories, but the heat exchangers, one company came forward to make the heat exchangers lightweight and high performance. For that, we have focused more on aerogels. And we bought an aerogel blanket from industry, so that that will be the benchmark, and we can also make products similar to that. And it is nothing but the aerogels are embedded in a glass wool matrix. And glass wool, as you know, that glass wool is an excellent low thermal conducting thermal insulation blanket, which is having a temperature stability of up to 600 degrees Celsius. Okay, so this aerogel was introduced in the blanket, and we have also studied in line with this results. We have also studied some of the applications. So this is also showing a commercial aerogel blankets which are used for insulation application, and it's all commercial only. We found that some of them are calcium silicate, and as far as high temperature is concerned, calcium silicate won't work. And my purpose is to find out the refractories for 1800 to 2200 degrees Celsius. So we prepared lanthanum phosphate, we also prepared boehmite, and we blended these two. Very interestingly, we have characterized everything. And lanthanum phosphate and lanthanum boehmite, they have a rod and viscous type microstructure in the TEM and SEM behavior. and such kind of needle-like, fibrous-like morphology is extremely important, and that will impart the strength as well as porosity control. So we have made a super thermal insulation glass fiber blanket, and you can see this is the processing stage using lanthanum phosphate, and we could successfully make this glass fiber mat, which is a super thermal insulator, and we have also put that in a Bunsen burner, and you see in the hot stove also we put, while burning of the stove takes place, we can touch the top surface of the blanket. So it's nothing but a super thermal insulation glass wool, and we have documented all the required parameters, and this is nothing but glass, that the other one is glass fiber, this one is a glass wool, and here also we have reached up to 900 degrees Celsius, and altogether the rare earth phosphate and rare earth pigment, rare earth modified pigments, they are all extremely important advanced material, and for the last 10-20 years we are working on rare earth varistors, rare earth superconductors, rare earth coatings, rare earth functional material, rare earth modified cement. Everywhere we are there, and we worked very closely with industry for the last 10-15 years. And this is an end of my presentation. And thank you very much for your patience listening. If any doubt is there, please ask me, I will clarify.
Thank you, sir.
Yeah.
Dear participants, it's your turn to ask questions, or you may raise your queries about this session. You can unmute your mic or may post your questions on the chat box.
I hope all of you got some idea. How can we explore the rare earth for multifunctional? Actually, in our laboratory, scientists are working on rare earth phosphors, rare earth luminescent materials, rare earth added alloys, scandium extraction, gallium extraction, and rare earth composites, rare earth ceramics. And if any one of you are really interested to come here and stay here for a month by paying a money, you can definitely, I can support you. You can come here, you can stay here, and you can also make some sensible data, and you can go back for and submit some papers. This is a good news that I would like to give you.
Thanks, sir. So we have a question in chat box.
Yeah.
What challenges are associated with the supply chain and sustainability of rare earth materials for industrial use?
Fantastic, fantastic. Actually, today, as far as the rare earth is concerned, our IREL is the only institute, government recognized institute, who can sell and who can buy the rare earths. We have star rare earths, and the earlier star rare earths was functioning based on the Chinese products, but today China also is not giving the rare earths to us. But as far as lanthanum oxide, cerium oxide and all concerned, we have plenty of resources. We have a very good monazite, we have very good rare earth containing, that means secondary resources, but material like scandium, gallium, molybdenum, gadolinium, we don't have any reserve, and only the secondary resources are there, especially from the spent batteries as well as spent electronic items. So your question is very, very valid. We are not having an adequate supply of rare earths, but lanthanum oxide, cerium oxide, zirconium oxide, and yttrium oxide, there won't be any dearth. You will easily get these powders.
So we have one more question.
Yeah.
Mention some advantages of using rare earth additives in metallurgy.
Why not? For example, you all know about Rafale fighter flight. Why? Well, see, actually, during the Manmohan Singh government also, we bought a Rafale. At that time, the cost of the Rafale was something. And then during the Modi time also, Prime Minister Modi time also, we bought the Rafale. This time, the price was doubled. Why? What is the reason? You will not understand. Scandium when a scandium is alloyed with aluminium, we are going to get high strength, high temperature stable, lightweight aluminium alloy. Only scandium can do. So that is the reason the price of the superjet missile is also very expensive, very expensive when we bought the second time. So second time the fighter jet that was having an aluminium body but with scandium. So you can work on any alloy material, you can dope any rare earth and you can understand what is the grain size control, what is the fracture behavior, what is the mechanical strength, how the rare earth additions are helping in making the engineered alloys, everything you can explore. So many people are working in my institute in this line. Any more question?
Participants, do you have any more questions?
If there are no questions, please, first of all, please do not hesitate to ask any questions. I am there to answer. And if you have a dream of working on the rare earths or advanced materials, you have an UV spectrophotometer, you have photoluminescence analyzer, you also should have a XRD, and you should have XPS. And if you don't have all these facilities in your lab, kindly like-minded people please come together and jointly propose a project to DST, and you make your own facility so that every one of you can take more PhD students and you can grow the field. And IREL has a limited scope. They will not give a project for the facility creation, but DST can give a facility creation project. And please propose a very useful, very niche area project so that it can be considered for funding. Thank you very much.
Thank you, sir.
Thank you. Thank you. Bye-bye.
On behalf of the organizing committee and all the participants of FDP, I extend my sincere thanks, heartfelt thanks to our distinguished resource person, Dr. Anandakumar S. So your talk has enriched our understanding about the session and for delivering an exceptionally informative and insightful talk on the topic rare earth-based functional materials. It provides immense value to all participants. And once again, thank you, sir, for your esteemed presence and valuable time for sharing.
Thank you. Thank you very much. Yeah, I hope that you get some benefit. Thank you very much. All the best. God bless you.
Thanks.
Yeah, bye-bye. Bye-bye.
Dear participants, now we are moving to our valedictory session. As we come to the conclusion of this enriching faculty development program, it gives me immense pleasure to stand before you during this valedictory session. Over the past 6 days, this FTP has truly been a journey of learning, reflection, and collaboration and professional growth. And first and foremost, I would like to express our heartfelt gratitude to our respected resource persons, experts, all the participants. As we conclude, let us carry forward the insights gained, implement innovative practices, and continue striving for excellence in teaching and research. May this FDP not be an end, but a beginning of continuous learning and collaboration and growth. Once again, I thank everyone who contributed to the success of this program. I wish you all continued success in your academic and professional endeavors. Thank you and have a wonderful day ahead.
Thank you very much. Bye-bye.
Dear participants, the session is now on the end, and the assessment test will be conducted on the ATAL FTP portal. All participants are requested to attend the assessment test scheduled on ATAL portal. The test starts at 7 p.m. and ends at 8 p.m. All have to complete the test without fail.
Madam, it will start at 7 p.m. na?
Yes, sir.
Okay, so we have to go through this assessment through the ATAL portal, not here.
Yes, sir. ATAL portal. You have to log into your ATAL portal profile on the portal.
Okay, thank you. So should we what next? What we have to do? Hello.
Dear
Hello.
participants, it's like multiple choice questions. Total number of questions included in the assessment is 25. So hope we have lavish time to complete the assessment because it's simple objective questions alone. No need to worry about it. And the session, assessment time starts at 7. You have to log in into your individual ATAL portal. There you can able to find the tabs like test. There you have to make the, you have to attend the test. Then after completion of test, then you have to submit the feedback, which is all available in the left side of your ATAL portal. So then after completing the feedback, then you can able to download your certificates.
Okay, sir.
So we
Got
will,
it. Got it, sir.
yes, sir. We will give you informations and updates through our program WhatsApp channel. So no need to worry about it. And once again, as a program coordinator, myself, Dr. K. Sargunan, on behalf of our organizing committee, I would like to thank, first of all the participants participated in the program for the past 6 days. So in spite of your official timings and so late evenings, you attended the program, and it's very, I hope the sessions were very informative. And the total on total till date we attended 13 sessions, so in which various guest speakers from various reputed institutions participated. I hope the sessions were effective, and so let me thank all the participants once again, and on behalf of management and participants, I would like to thank the organizing team. I would like to mention the names also. Miss Nayana and Miss Adina from Civil Department, and Miss um, Anju and Miss Aditya from Applied Science Department. I would like to thank them on behalf of all the participants and the Civil Engineering Department of Vidya Academy of Science and Technology Technical Campus. Once again, all the best, and very thank you to all the participants and the team. Thank you.
எது விக்கின்னு ரித்விகா அதெல்லாம் நிறைய இருக்கு.